Do you hear me okay? Yep. Okay, good morning, everybody. Today is the third day. This course. We made a long way. We have another long way. And today we will continue the story of. I don't hear myself well. Today we continue the story about the environment and nanotechnology. We will start with a very interesting sub um, sub-subject, which is called nanobiotechnology, which is essentially the interface between the nanotechnology and the biotechnology world. And we will see how this is affecting our understanding of biotechnology. What we will talk about today, we will discuss antimicrobial nanoparticles, how they help, um, how they help our dealing with the environment. Then we will talk about carbon dots again. As you see, I really like carbon dots. This is part of my expertise. We will talk about carbon dots for bacterial imaging and degradation. And then we will describe a interesting application of carbon dots for antiviral face masks. I don't think this is working well. Maybe I'll stand like this. Or I can talk with this. attached to the surfaces. Usually bacteria have a surface which is positively charged. So what you need to take metal nanoparticles and coat them with some molecules with negative charge. Then you're going to have attraction, positive bacteria, negative nanoparticles, and they bind together. And why do you want metal nanoparticles? When you have metal nanoparticles, you can apply a very useful analytical technique, spectroscopic technique called SIRS. SIRS is a technique, is an abbreviation for Surface Enhanced Raman Spectroscopy. Raman spectroscopy, for those of you who don't know, it's a very sensitive technique that gives you signal from metal regions, from metal areas. So if we have metal nanoparticles bind to bacterial surfaces and we apply SIRS, we apply Raman spectroscopy, then we have a Raman spectrum for the nanoparticles. Now each nanoparticle will have a different Raman spectrum depending also on the environment. So if the nanoparticles sit on the surface, spectrum, if the nanoparticle sits on this bacteria, we're going to have a different spectrum. That's how, by using nanoparticles, metallic nanoparticles, we can get specific Raman spectra for specific bacteria. And that's how we're going to be able to identify the bacteria and tell ourselves, here there is bacterial contamination, and here we don't have bacterial contamination. This is another example of using nanoparticles for bacterial imaging and also killing. What we do here we attach to the bacteria's surface gold nanoparticles. On the left, we attach spherical gold nanoparticles. On the right, we attach rod-like gold nanoparticles. Now, why it is important? Because in certain shapes of gold nanoparticles, and actually other types of nanoparticles, what we can do, we can irradiate with infrared light. And when you have rod-shaped gold nanoparticles, they absorb the infrared light. What is infrared light? You know? Where does it come from? From sun, but also from the body. Infrared light, in general, comes from heat. When something emits infrared, it means that it is hot. So if these nanoparticles will absorb infrared light, what it does, it simply heat the nanoparticles. Now if you absorb infrared and you heat the nanoparticles, and you heat more nanoparticles and more, and the nanoparticle sits on the surface of the bacteria, what happens eventually? The bacteria will die. You simply burn the bacteria using IR, infrared light, shining on the bacteria, absorbing by the rod-shaped nanoparticles, and killing the bacteria. So these are very nice examples of using nanoparticles particularly metal nanoparticles, gold nanoparticles, both for imaging or for seeing bacteria through Raman spectroscopy, also killing bacteria through the thermal effect, through heating and burning the bacteria. Actually, the concept of using nanoparticle for killing bacteria, the antimicrobial metal nanoparticles, is a very big concept. It's a very big field of research. And actually, many people, and there are actually also commercial products for using silver nanoparticles as antimicrobial agents. You will actually find coatings for surfaces made from silver nanoparticles that are used for antibacterial effects. In hospitals, for example, in instruments surgeons use, often they coat them with silver nanoparticles, and this makes them very antimicrobial. The reason actually is not entirely clear, but what we think is happening is that silver nanoparticles have many electrons that are free. Why they are free? Because silver is a metal. And in metals, we have a lot of electrons on the surface of the metal. Now, if we have many electrons on the surface and bacteria coming, the electrons can oxidize the bacteria or reduce the bacteria or go into the bacteria and disrupt biochemical processes. What people found is that in silver nanoparticles in particular, this redox effect, this electronic effect is very strong. Maybe because in silver nanoparticles, the electrons are free, are more free than other nanoparticles. Anyway, the thing is that silver nanoparticles are very useful as antimicrobial agents, and you can actually design various products using silver nanoparticle for antimicrobial activity. The other thing is actually it's very easy to make silver nanoparticles, and they're very cheap, relatively speaking. That's why people use them for antimicrobial applications. These are some examples of what silver nanoparticles can do in bacteria. This is a general shape of bacteria. We have the DNA, we have proteins and enzymes inside the bacteria. And here we can see what the silver nanoparticle can do. These are the silver nanoparticles. You see that they are very small. If they're very small, they can go into the bacterial cell very easily. And then when they're inside the bacterial cell, using this redox effect, the reduction oxidation effect of the electrons, they can do damage. They can damage the DNA. They can affect biochemical processes of enzymes. They can break the membrane. They can destroy other proteins, membrane proteins, or proteins inside the bacteria. Overall, they are very effective in killing bacteria. So silver nanoparticles as antimicrobial agents. Now, we talked about silver nanoparticles, but these mechanisms of antimicrobial activity are very general for many types of nanoparticles, not only silver and actually not only metal nanoparticles. So whenever we have nanoparticles and they can go into the bacteria, inside the bacterial cells, they can do a lot of damage. They can do a lot of damage everywhere, in all the different molecules, organelles, different parts of the bacterial cell. One particularly interesting effect of metal nanoparticles is on the bacterial biofilm. Have you heard of the bacterial biofilm? You know, the reason bacteria in our body are so bad, it's not only because bacteria themselves are bad. It's because bacteria, when they go into our body, they form what's called a biofilm. A biofilm is like a shield. It's a matrix. It's like a building that bacteria build above themselves. And by doing this, it protects them from the body. You know, the body is very good in preventing infection, in preventing attack by bacteria or by viruses. How the body does that? The body has the immune mechanism. When something goes into our body, some foreign thing, viruses, bacteria, proteins, anything foreign that comes to our body, the body immediately gets into action. It secretes proteins, it has cells, white blood cells, other types of immune mechanism and immune proteins that go very fast to the foreign object and destroy it. That's why our body is very good on surviving in this world with all the bad things that are around us. So what would the bacteria do to prevent this attack by the body? What they do, they have this shield that they build around themselves. Now this shield is made of very strong proteins and sugars. So when you have this shield, this biofilm, the bacteria actually is sitting here inside this shield, and nothing goes in, and the bacteria are happy. They can proliferate, they can grow. The body cannot affect them. And after they grow, and you have millions of bacteria inside this biofilm, then they go out, and for the body, it's much more difficult to fight millions of bacteria. And then you're sick. You know where else we have biofilm? In our teeth. You know why we have holes in our teeth? We brush our teeth every morning and every afternoon maybe. But still, if you're a dentist, you have lots of work. You have holes in your teeth. The reason is biofilm. When bacteria go on your teeth, immediately they form this shield. And then when you have their shield, this biofilm, you can brush your teeth 3 times a day and it will not help. Because the biofilm protects the bacteria. So then you have biofilm in your teeth. And the bacteria are very happy. They proliferate and they start making holes in our teeth. That's exactly why we have holes. Some bacteria have big biofilm and some bacteria have small biofilm. But this is the reason And one of the main reasons why bacteria are very bad for us. But luckily, we have nanoparticles. So these are the bacteria in our teeth, the biofilm in our teeth. Now, how can nanoparticles help us with the bacterial biofilm? Now, the interesting thing is, this is another example of biofilm. The interesting thing is that some nanoparticles can penetrate this shield, this biofilm, and kill the bacteria even inside the biofilm. For example, the silver nanoparticle. Silver nanoparticles, surprisingly, they can go inside the biofilm. This is the matrix of the biofilm. They can slowly break the biofilm and reach the bacteria under the biofilm. People still don't know exactly how it happens, but when the silver nanoparticle destroy the biofilm, the bacteria are no longer protected. And that's how we can kill the bacteria, by the silver nanoparticles or the immune mechanism of the body. Now this looks very nice, but it's not so simple, because silver itself is toxic. We don't want to start swallowing silver into our body, because silver by itself might cause damage to our body. So this is, it's always positive things and negative things. If we can find a drug, a treatment that will use this silver nanoparticle effect of destroying the biofilm and still not be toxic, not be bad to our body, this will be a very interesting and effective way to fight bacteria. Let's describe another interesting application of nanomaterials, nanotechnology, for fighting bacteria. In the example here, something that we did in my lab several years ago, we used carbon dots, both for imaging bacteria and also for killing bacteria. Now, the bacteria that we study is called Pseudomonas aeruginosa. Pseudomonas aeruginosa is a very bad bacteria. It gives us pneumonia. It's involved in many really bad infections. If you type in Google Pseudomonas aeruginosa, you will find not so nice pictures of people sick with various diseases. So we definitely want to know if people have Pseudomonas aeruginosa in their bodies, and we want to know if we can kill these bacteria, these Pseudomonas aeruginosa. These are just some of the ugly pictures that you find in the internet about Pseudomonas aeruginosa. Okay, you see somebody here with infection in the lung, just like pneumonia. Here you have some infection of the skin with Pseudomonas aeruginosa. Anyway, I wish you all good health, so you will not have Pseudomonas, but we will try to help you and people in general with identifying and killing Pseudomonas aeruginosa. Now, another very bad problem with Pseudomonas and other bacteria is something that is called multi-drug resistance. You heard this term, multi-drug resistance? You know, some bacteria develop resistance against antibiotic compounds because of evolution. We give ourselves penicillin and various other antibiotics, but the bacteria learn how to deal with that. And this is actually very dangerous because as time goes by, there is bacteria that can resist antibiotics. And then we cannot do anything to treat disease. So this is another good reason why we want to find new ways to kill bacteria, new antimicrobial agents. So here we go back to the carbon dots. Remember our carbon dots, which we talked about several times the last couple of days? Just reminding you why we like carbon dots. We like carbon dots because of the colors. And we have colors because of the surface of the carbon dots. Now the interesting things about carbon dots is that it's very easy to control the surface of the carbon dots. We can actually put on the surface or generate on the surface various different chemical groups. And by doing that, we can have the carbon dots go into specific locations and into specific cells. How we do that? For that, we need to look more carefully on the surface of bacteria. Now, bacteria have very interesting surface properties. Bacteria which belong to the gram-negative family. There are two main types of bacteria in the world. Gram-negative and gram-positive. In both cases, you can find good bacteria and bad bacteria. Now remember when we talked about Pseudomonas aeruginosa, Pseudomonas aeruginosa belong to the gram-negative family of bacteria. Now, what we know about gram-negative bacteria is that the surface of the gram-negative bacteria have lots of sugars and also a special types of lipid which are called lipopolysaccharides. These are lipids with sugar on top. And these lipopolysaccharides are very specific to gram-negative, and even more than that, Pseudomonas aeruginosa have specific lipopolysaccharides or LPS on their surface. Now, in this project, this was very good for us because it gave us a target for binding carbon dots through the lipopolysaccharides on the surface of the bacteria. So this is the structure of LPS, lipopolysaccharide. Okay, you see the lipids here, and then there's a connector and a very long chain of polysaccharides, sugars. So what we're going to do with this? What we can do is we can make carbon dots with special surface. We will take, remember, the way we make carbon dots is that we take some carbon source and we heat it to a about 100 degrees or 150 degrees. So what we made carbon dots from two carbon sources. One of them was citric acid, what we find in lemon, okay? Very cheap, very easy. And then we took another small molecule called aminoguanidine. Now we did not need to take specifically aminoguanidine, but what we need and what aminoguanidine gave us is these units, the amino units. And when we make the carbon dots, you see that these carbon dots have the aminoguanidine units on their surface. Now the special thing about aminoguanidine is that it recognizes and it binds very strongly this part of the lipopolysaccharide. So what we accomplished is carbon dots that will bind specifically to the surface of the Pseudomonas aeruginosa bacteria through the interaction between aminoguanidine and the lipopolysaccharide. So let's see what happens. In this case, we use E. coli bacteria, okay? We use E. coli bacteria, which is also a negative type of bacteria, gram-negative bacteria. We added the carbon dots with the aminoguanidine, and this is what we get. Remember the color of the carbon dots, the beautiful color of the carbon dots. Now what we did, we simply mixed the solution of the carbon dots with the bacteria. The bacteria actually didn't care. They just grew. But the carbon dots were attached to the surface of the bacteria through the interactions between the aminoguanidine and the LPS, and we get bacteria with color. This is not a visible color, this is a fluorescent color. And still, you can look at the microscope using a fluorescent microscope, which is also something very simple and cheap, and you can see the bacteria. So think about it. If you're sick, you go to the doctor, and the doctor can take some swab from your throat or some blood, and the doctor puts it on a plate with the carbon dots. You wait 1 hour, 2 hours, and then you look at the microscope. If you have infection, you can see the bacteria very clearly, very nice color. It means you're sick. If the doctor doesn't see anything, everything is good. And actually, what you can do not just seeing the bacteria, you can also kill the bacteria. If you put a lot of carbon dots with the aminoguanidine. The aminoguanidine carbon dots will bind to the cell, to the Pseudomonas aeruginosa cell, and kill the bacteria. Because the bacteria doesn't like so many small carbon nanoparticles bind to the surface and affect the biochemical processes on the surface of the bacteria. So these are electron microscopy images, okay? These are the Pseudomonas bacteria. You see the rod shape. This is control without carbon dots. Here we added the carbon dots and we waited 30 minutes. You see that all these are dead cells. Carbon dots kill
the bacteria. Now, this technique is very specific to gram-negative bacteria and more specifically to Pseudomonas aeruginosa. Because if you do this with another type of bacteria, this is a bacteria called Staphylococcus aureus. This is also a not so friendly bacteria. You don't want to have Staphylococcus in your body. But this is different disease. And the thing with Staphylococcus aureus, it's not a gram-negative bacteria, it's a gram-positive bacteria. And gram-positive bacteria don't have the LPS in their surface. So, carbon dots with the guanidine head group cannot bind to Staphylococcus surface. So when we mix Staphylococcus bacteria with the carbon dots, nothing happens. Because the carbon dots cannot bind to the surface of this bacteria. So what we see here is a very nice way to use carbon dots as specific drugs, specific antimicrobial agents against Pseudomonas aeruginosa. And we can use the same concept for targeting other types of bacteria because it's very easy to control the surface of the carbon dots. We can put in the surface of the carbon dots different molecules that will recognize other types of bacteria. So this is a story about antimicrobial carbon dots. Actually, we can, because it's so simple to make carbon dots, we can use them in different products to give them the antimicrobial properties. This is just a dream. Okay? There's no products yet, but it's certainly possible. We can make antimicrobial cream. Let's say you have a wound with bacterial infection, so you can make carbon dots. The same carbon dot that I showed you before, you mix it with something and you're going to have a cream. A cream which will be antibacterial. This is a story about antimicrobial carbon dots. Let me tell you another story about antiviral effect of carbon dots. Actually, this project started in the COVID days. Remember the bad days of COVID? The terrible days of COVID? Just like a nightmare, we all try to forget it. But for me at least, part of the nightmare of COVID was, I don't know how it was in India, but in Israel, for maybe 1 year, they wanted you to wear face mask. And I hate face masks. So anyway, because of this requirement to wear a face mask, we thought of this project of making special face masks with carbon dots that will help us fighting COVID and other types of viruses. And the story here actually is related to, remember yesterday when we talked about the photothermal effect of carbon dots? You shine light, you get heat. That's the simple concept that we used in this system, in the story of antiviral face masks. So this is the face mask we fabricated. Okay? We took carbon dots Okay? We mix them with a certain polymer that will help them stick together and form a film. And then we add them to a very thin polymer layer. So we have a polymer with carbon dots inside. Now the polymer layer was very thin and used a special polymer that has pores. See my picture? Yes. This is the polymer. This is this polymer. And this polymer has lots of pores with carbon dots. Now why it is important to have many pores? What? We need to breathe. We need air to come in. So if we put something without pores, we're not going to have enough air. So it's very important, if we want to have this on our face mask, that it will be porous, that it will let air coming in and out. So we have this thin film of polymer with the carbon dots. And now we put this on a simple cotton face mask, same cotton that we use, and then we can walk outside. When the sun will heat, will shine and put light on this polymer layer, what will happen? There are carbon dots there. The carbon dots are going to absorb light. The light that the carbon dots absorb becomes heat. And viruses, just like any creature in the world, they don't like heat. When you heat them, they will die. Okay? So when you're exposed to sun, you will simply kill the viruses through heating the polymer layer. Now you might ask me, okay, if you have this photothermal effect, you will burn your mouth because it's going to be hot. So that's also not very attractive. But the thing is, you put the polymer on top of the mask. So we actually made these face masks. We use them in the lab. So the cotton is sitting here, you don't feel the heat of the polymer. And the polymer layer is very thin. So it's enough just to heat the polymer layer so the viruses will die, but it does not hurt our body. So this is how it looks like. And again, the same story about photothermal effect of the carbon dots, the heat released in opposed to a shining light. And this is actually what we got. What we see here is the infrared camera. Remember, these are pictures from a infrared camera that is sensitive to temperature. The more red the color, the higher the temperature. And what we see here, this is the pictures from the camera of the polymer face mask with the carbon dots. And this is just the carbon dots this is just the polymer without the carbon dots. Okay? Now without the carbon dots, see, we heat 20 minutes, we expose to the sun for 20 minutes. After initially 27 degrees, we expose to the sun 5 minutes, we get 33 degrees. After 20 minutes, 41 degrees. Now what happened when we have carbon dots there? We start with 28 degrees. After 5 minutes, we already reach 58 degrees. After 20 minutes, we have 66 degrees. Now, 66 degrees, 66 degrees here is very bad for the viruses. When the viruses experience 66 degrees, they die. People don't like 66 degrees. Viruses also don't like 66 degrees. So what we get is killing of the virus through the temperature. Now, with a face mask, you want to wear it for several hours. It's not only one time. So what you can see here is that we can actually cycle it. Many, many cycles, 30 cycles. We shine light, the temperature goes up. We turn off the light, goes down. Up, down, up, down. We can do hundreds of cycles. The face mask will be good. Thank you. Oh, questions? Oh, sure.
Hello, thank you, Professor Raj. I now request the participants to put up their questions, if any. You can ask question if you have.
Yes.
Thank you for your lecture. I want to ask the question that what is the reason for what is the driving force for the nucleation of the metal ions, and why they are converting into so small size? This is a nanoparticle.
Why the metal ion converting to? Again, please ask the question again.
We are using the reducing agent. The metal is going to the zero oxidation state.
Exactly.
Then what is the reason that it is becoming so small, so nano size?
Okay, that's a very nice question. I'll repeat the question again, and I hope I understand the question. To make nanoparticles, we take metal ions and we reduce them with a reducing agent, and we get the metal zero. Now, the question is, if I understand correctly, you're asking why the metal zero go together and make small nanoparticles? Okay. You know, in nature, it's very rare to find individual metal atoms just floating around. It is not a stable state. It's not a coincidence that in nature you mostly have the ions, because metals like to release electrons. In order to have stability of individual metal atoms, they need to stick together. Then you have the forces between the metal atoms in order to form small clusters, small aggregates, which are the nanoparticles. So thermodynamically, it's more stable to have small aggregates of metal atoms.
Next.
First of all, thank you, sir, for the lecture. Sir, from yesterday onwards, we are talking about the photothermal effect of carbon dots. So, sir, my question is, how sensitive are carbon dots to photothermal effect? Means, what should be the intensity of the sunlight to initiate this entire process?
Okay. You know, carbon dots will always have the photothermal effect. How sensitive it is depends on the carbon dots themselves. Some carbon dots absorb light and release heat more efficiently. In some other cases, it's less efficient. The most important factor for this photothermal effect is how good the the carbon dots absorb light. And this depends on what we call the absorbance spectrum. You know UV vis absorbance spectroscopy? There is I wish I could have it, but there is an absorbance of particles of light in different wavelengths. If you take carbon dots that have very good absorbance, very efficient absorbance of light in the visible region, then you have a very strong photothermal effect. Sometimes you have carbon dots that do not absorb so well, you have less efficient photothermal effect. This is the most important parameter. Of course, other parameters is the intensity of light that we use, the concentration of the carbon dots that we use. These are also important parameters.
Sir, in case of the bacteria. Namaste. Thank you, sir, for nice informative lecture. In case of bacteria, the silver nanoparticle is penetrating the wall of the bacteria and destroying the DNA molecule.
For example, yes.
Yeah, you have shown there. So, is it any evidence like the membrane pore size is larger than silver nanoparticle and they are able to penetrate and go inside and interact with DNA, or it is proposed mechanism?
Actually, we know, scientists found carbon dots inside bacteria. So this is a fact that they go inside. Now, if they go inside, they can do many bad things. Bacteria can take various things inside from outside. This is something well known. There are proteins on the membrane of the bacteria that they take things from outside and they bring inside. Silver nanoparticles are very bad for the bacteria, but they can still go inside and do damage on the DNA and other things.
Sir, very nice lecture. Thank you very much for delivering the lecture. Just like for antibacterial, you are showing the carbon dot with guanidine group.
Yes.
Right? Guanidine group. So that was derivatized, that was synthesized in laboratory.
This is a very good question. The answer is no. Actually, the nice thing about the carbon dots is that you can take different building blocks, different precursors, and because you use a relatively low temperature, the carbon dots that you get will contain on their surface the structure of the building blocks. This is really what makes carbon dots so interesting. Because if you take carbon or these molecules and you apply very high temperature, you're doing pyrolysis, then you kill all the chemistry. You kill all the chemical structures. But with carbon dots, because you do this in very mild conditions, you get carbon dots with the surface without doing anything else. You don't need to do complicated chemistry.
What's the use of ascorbic citric acid?
Citric acid actually is a well-known component of carbon dots. Most carbon dots, or not most, many carbon dots use citric acid. It's a very common sugar, very cheap, and it gives you the core of the carbon dots.
And the same carbon dots being used for antiviral properties?
No. For antiviral, we use different carbon dots. What we wanted from these carbon dots is that the question that was asked before, we wanted them to have very good absorbance of light. So that's why we used, it was even simpler carbon dots in the antiviral face mask project.
Thank you.
question.
Thank you, sir, for the nice talk. So I have a query. Like here, you are using carbon dot as a template for stabilizing silver nanoparticles.
No.
It's on the surface you are using carbon dots.
What project you talking about?
Suppose this one.
There's no silver, just carbon.
And the silver nanoparticles. What are the templates and how is the stability?
The silver nanoparticles is not my work. People just use silver nanoparticles as antibacterial agents without any template. Take silver nanoparticles, you add to bacteria, and they kill bacteria through this redox effect, through the electrons on the silver nanoparticles. So there's no template.
But silver nanoparticles has some stability issues because it is like degrades in presence of light. So in this case, so in carbon dot case, so what is the stability in presence of light, heat, or other conditions?
They are very stable actually.
So it does not degrade.
I'm sorry?
It does not degrade in presence of light.
Well, after few days or months, they can degrade, but they are very stable. That's actually one of the nice things about carbon dots. They are very stable.
Thank you, sir.
Can we increase the volume? I feel that I'm losing my voice.
One more, the mask you have
Yes.
produced with PVDF
Yes.
simple,
Okay.
right? And then you are going to embed this carbon dots inside
Yes.
the film. So what's the pore size of this polymeric film?
The pore sizes. The pore size is actually in the tens of the micron range.
So is there any chance when we are inhaling some carbon dot may get?
Excellent question. What we find was that the carbon dots are attached to the surface here very strongly.
Chemically or
Actually, no, can be physically, but it's very strong and they don't leach out. They are very stable, so once we prepare them, they stay there. They don't come out.
Good work.
Thank you. I think now the House will undergo 10 minutes recess.
Sure.
And the lecture will resume. The second lecture, today's second lecture will resume after 10 minutes. Thank you.
You know, maybe I'll use this.
sir? Hello. Sir, अब आ रही है, चेक करिए। हेलो। 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 हेलो, माइक टेस्टिंग, हेलो। 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 अब क्लियर है। मैंने तो पहले स्टिक करके भी सेटिंग करना चाह रही थी, लेकिन उसके बाद वो डाल दी ना। हेलो। 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 कम, हाँ स्ट्रीम में देखो इसकी क्योंकि कम आ रही है, इसकी आवाज़ भी थोड़ी सी ज़्यादा कर दो। वॉल्यूम ए, वॉल्यूम बी, वही जो छोटा वाला जो नीचे कुर्सी पे लगाया हुआ है, चेयर पे। हाँ जी। वॉल्यूम वन, वॉल्यूम टू, दोनों मिनिमम पे है। हेलो। हेलो। ओके।
You think it's working?
Yes, I tried my best.
You heard yourself.
Welcome back for the second lecture of the day, and I guess in total this is seventh lecture on the topic of nanotechnology and climate change. Or you need something?
No,
Okay.
Okay. Start? Yes. Sure. Thank you. Okay. Oh, no signal.
होगा सर स्टार्ट ऑन आप किए हैं आ जाएगा।
Okay, welcome back. We are making a big switch from bacteria, from viruses, from biology, and we will talk now for 2 lectures on a very big subject, huge subject, which is called energy. Now, this is such a big subject that we cannot cover everything. Nanotechnology has many applications for the energy world. We cannot really talk about everything, but what I hope to do will give you some ideas what nanotechnology can contribute, how it can help our energy applications, particularly alternative energies, both solar energy, which is very important if we want to survive in this world, and also energy storage, batteries, for example, which is also very important for the energy applications. So this lecture we will discuss 2 things. The first subject will be talking about conductive nanowires. We need to talk about conductivity because anything with energy has to go with electricity. And electricity requires conductivity. So we're going to talk about conductive nanowires. Then we will talk about solar cells. Again, solar cells is a huge field. We're going to talk about 3 different subsections in the solar cell field, which is dye-sensitized solar cells, semiconductor quantum dots in solar cells, and some discussion of green solar cells. Now, nanowires. Why do we want nanowires? We're all talking about smaller and smaller computer. We all want our cell phones to have more and more data. We want to have computers that can give us beautiful pictures and videos and movies and whatever. All these things need electricity. All these things need to carry electrons from one place to another place. That's how electronics work. So we definitely need small things, small features. And if we have nanowires, this will be very good as parts of electronic circuits. Very small electronic circuits. This is just an example of making metal nanowires. Now, why do we want metal? Because they are conductive, okay? There are many ways to make metal nanowires. Here, this is just one example of making metal nanowires. We start with ions, which we reduce. Then they nucleate and make seeds. And then we can take the seeds and attach them together side by side until they make metal nanowires. There's other techniques to make metal nanowires. Overall, you can see we end up with a long wire. All these things here, these dots, are single atoms of metals. Now, as I said, we definitely need those metal nanowires in electrical miniaturization to make small and small electronic circuits, See, this is just an image of a circuit that you can find, for example, in your computer. You see here, all these are wires. So if you want to make something small, we need small wires. We need these wires to be nano wires. So metal nanowire technology is critical for the new world of microelectronics and nanoelectronics. For example, our cell phone. If you look at the screen of our cell phone, the screen of our cell phone is actually conductive and it's also transparent. It is one of the technologies that people use in the screens of cell phone is made of silver nanowires. Now, because they are nanowires, they allow electricity to go through. Because they are so thin, they don't block the light. And that's why we can see the screen very easily. So just a beautiful example for nanotechnology, nanowires in electronics. Another reason we like nanowires and we need to use nanowires is the issue of heat dissipation. You know, heat in electronic circuits is a big problem. When you have small wires and you have electricity going through, the wires get hot. That's a natural phenomenon. Electrons also generate heat. Now, if we have a very small circuit with many, many, many wires and they're all getting hot, it can burn the circuit. It can burn our computer. It can burn the small electronic components. This is really a big problem in electronics. Now, if we make and if we use nanowires, we minimize this problem of heating because the nanowires are so small and there's a little amount of heat generated and we're in good shape. So these are very good reasons, very important reasons that nanowire technology is very important to microelectronics and nanoelectronics. And all the electronics companies, Samsung, Apple, all these companies are investing billions of dollars to make small nanowires that will be conductive, not generating heat, and take very little space. Let's switch subjects and talk about nanotechnology and solar cells. So as I said before, this is a huge, huge field. Lots of different technologies, different developments. Okay? And I'm going to give you very few examples of the relationship between nanotechnology and solar cell technology. Now, what do we need in solar cells? The basic concept of solar cell is very simple. We take light, we shine light, and what we want when we shine light, we want to generate electrons that will go from one electrode to another electrode. That's all what we need in solar cells. Shining light, and when you shine light, you have electrons. When you have electrons, you have electricity. Now, even if this sounds so simple, the actual thing, how to get electrons when you shine light, this can be quite complicated. And there are many technologies to do this. Shine light, generate electrons. And what I'll tell you is how nanotechnology can help this process of shining light and generating electrons. Now, some of the concept here might be a little complicated. Don't worry if you don't understand. But if you just understand the reason why we want nanotechnology in solar cells, by itself, this is going to be okay. So this is the basic concept of a solar cell. We have one electrode, we have another electrode. Usually the sun comes from one electrode, so this electrode usually needs to be transparent, okay? The bottom electrode does not need to be transparent, but all these electrodes, they need to be, or particularly both these electrodes need to be conductive, okay? Now, one of the most important parts of the solar cell is here. This is called the emitter. The emitter is a material that when you shine light, it emits electrons. Now, it sounds very simple and very easy. It's not so easy. And what nanotechnology can help us is designing emitters that will be very efficient and very good and very stable. Because this is the secret of solar cell technology. If you have good emitters, you have good solar cells. If you have emitters which are not so efficient, the solar cell that you make is not going to be so good for generating electricity. Now, the emitter generates electrons. This is an electron. Now, when the emitter generates electron, it's also generating a hole. The electron is negative. When it goes out of the emitter, you have a hole left behind, a positive hole. The problem with solar cells is that the electron combines with the hole and does not get to this electron. What we want in a good solar cell is electron generating in the emitter. It will go all the way to the other electron, and then it will go back. And when the electron will go back, we have energy. We have light. We have the air condition. We have anything we want to do with electricity. So this is the basic scheme of the solar cell. Let's see how nanotechnology can help us here. Stop working. Okay. This is one example of nanomaterials in solar cell technology. This concept of solar cell called dye-sensitized solar cell. What we do here, we shine light through this electrode. When we shine light, we have nanoparticles of titanium oxide. Titanium oxide nanoparticles are very common in this type of solar cell. Because what the titanium oxide do, titanium oxide can absorb light and excite electrons to a high level, which then the electrons going into a high level, okay? You have the titanium dioxide, you generate electrons, and then the electrons reduce a dye molecule. Iodide is a dye ion. Why we call it a dye? Because the iodide take the electron and transforms into another molecule called 3-iodide. I minus to I3 minus. This is a reaction that happens with the electrons that are coming from titanium dioxide. Then what happens? The triiodide goes all the way, it reaches the bottom electron and releases the electron. Just like a car that takes the electrons from here to here. And again, if we do that, we close the circuit. We generate electrons here through light. The electrons go all the way here, and then they go back, and we can have energy, solar energy. Now, where nanotechnology is important here, in the titanium oxide nanoparticles. The titanium oxide nanoparticles are critical in the first step. They take light, excite electrons. Then the electrons can go and reduce the iodide into triiodide, which then go to the other electrode. Now, why people like titanium oxide here? Both because of the energy level, the excitation, but also because they have very high surface area. If you will put just a layer of titanium oxide film, it can still generate electrons, but not enough electrons. If you have many, many nanoparticles of titanium oxide, you can generate many electrons, and then you're going to have an efficient solar cell. So this is called a dye-sensitized solar cell. This technology actually is not so practical for large-scale solar cells. You know which is the material that is most popular in the solar cells that we use now in the field? Silicon. And we're going to see why silicon is so important. But still, this is a very interesting technology, more small scale, and it's a very nice example how nanotechnology can help us. This is just another example, another scheme of the same concept, dye-sensitized solar cell. This one shows you a little bit the energy levels of the system when you excite the electron in titanium oxide to a higher level, which then go to the dye, the mediator that takes the electrons from one side to the other side. Actually, in this case, it's the other way around, but that's okay. Another type of solar cells which uses nanoparticles can be shown here. It's called a nanoparticle heterojunction solar cell. Basically what we have here, we have nanoparticles that help, conductive nanoparticles, metal nanoparticles like silver, that helps to take the electron from one electrode to the other electrode. So they sit here in the active layer. After shining light, they shuttle the electron, or they help shuttle the electrons or the holes into the other electrode and generating energy. This is just another example of the same concept, calling a heterojunction solar cell, where we have a component, nanoparticles or molecule, that takes the electron, another one that accepts the electron and take it to the other electrode. The most important thing, as we said, We have the electrons going from one electrode to the other electrode. Nanoparticles can be very good in shuttling, carrying the electrons from one electrode to another electrode, which is what we do in solar cell. Now let's talk about the most important these days, the most popular solar cell technology, which is the silicon solar cell. This is the main basic concept of silicon solar cells. There is no nanotechnology here. But first I'd like to explain the concept. Now, what we have here again, we have the electrode that we shine light. This is the main part of the solar cell. And this is the electrode that takes the electrons. Remember, our goal is generate electrons here or induce electron here and get them to the back and close the circuit. Now, why silicon is so good about this concept? Why it's so popular? Silicon is what we call a semiconductor material. The nice thing about semiconductors is that they have relatively narrow energy level. This is a metal. In metal, electrons can move freely in the metal. So metals cannot help us in solar cells because you connect metal together, electrons will go freely until they're gone. We cannot generate electrons by light. Insulators, the energy level between the energy band gap, the distance between the electronic band and the conduction band, the top band, is very high. So in insulators, it's very hard to take electrons from here and move them here. That's why insulators are insulating. They prevent conductivity. Okay? So if we shine light on an insulator, nothing will happen because the electron cannot go up here and start moving. Semiconductor, on the other hand, are perfect for this job because the distance here between the electron band and the conductive band is relatively close, relatively small distance. And then what we have, when we shine light on the semiconductor, light can give us enough energy to move the electrons from here to here, and then we have generated electrons, generated free electrons. And that's exactly what happened with silicon. Silicon is so good because it's very easy when we shine light to get electrons from the lower band, from the valence band, to the conduction band, and then we can use the electrons. Okay? So when we have a solar cell, a silicon solar cell, we have many silicon atoms. Throughout the cell, we shine light, we shine solar light, and the electrons will jump from the valence band to conduction band of the silicon, and then we can use them. We can take the electrons and we can use them. We can use them for generating energy. Free electrons are energy. So this is why we like and we use silicon as a main material in solar cell. Now, how can nanotechnology help us in this concept? Silicon is semiconductor. The early days of nanotechnology, or the first invention in nanotechnology, were the semiconductor quantum dots. What are semiconductor quantum dots? We can have the same effect of a distance, or a good distance, between the valence band and the conduction band, not only with silicon atoms, but also with what we call semiconductor quantum dots. There are various semiconductor quantum dots from various materials, because many materials are semiconductors. And people found that when we take very small, nanometer size semiconductor material, they can have the same effect of a small valence band between the low energy and the high energy. So if we take semiconductor quantum dots instead of silicon, we can get the same effect. We can shine light, okay, and we can excite electrons from the lower level to a higher level and get free electrons, which is exactly what we want in solar cells. Now, what is the problem? Silicon is relatively cheap. Where we can find silicon? For example, in the sea sand. There's a lot of sand in the world. So practically, it's easy to make silicon. And this is actually the reason why all solar cells right now are made of silicon. But there are semiconductor quantum dots from various materials that can be made very cheaply and efficiently. And actually, one of the main challenges in this field of semiconductor quantum dots is just developing the technologies to make cheap carbon dots, cheap semiconductor quantum dots. If you make good semiconductor quantum dots in a cheap way, efficient way, in large quantities, you can compete with silicon solar cells. Let me just show you some examples of semiconductor quantum dots. Okay? In all these cases, there's various configurations of solar cells with quantum dots. Okay? Again, the concept is the same concept. One electrode here that's transparent, another electrode here that takes the electron. You shine light, you have quantum dots, semiconductor quantum dots. They generate electrons because they have low gap. And the electrons will go from here to here, and we're very happy because we have solar cell. Okay? So these are various specific configuration that we use for green solar cells. Now, semiconductor quantum dots are one of the possibilities to make new solar cell technologies. We can actually use the same concept, not with semiconductor quantum dots, but with other materials. Because you know, some of the problem with semiconductor quantum dots is that they can be toxic to produce. You know, some semiconductor quantum dots are made from really bad material. like cadmium. Cadmium sulfide are excellent semiconductor quantum dots. They can generate electrons, you can shine light, and you can move electrons from the low level to the high level extremely efficiently. But cadmium is very bad for you. So you cannot build factories that make cadmium sulfide quantum dots because the cadmium is extremely toxic and you don't want to release it to the environment. So you don't use cadmium sulfide. Another good element for semiconductor quantum dots is arsenic. You know arsenic, IS? Arsenic is a poison. So you can make gallium arsenide quantum dots that will be excellent for solar cells in terms of energy levels. But arsenic is very bad. Nobody wants to deal with arsenic. So this is really one of the biggest problems with semiconductor quantum dots. Silicon is not toxic, is not harmful to the environment. So no problem, we can use silicon. But if we use semiconductor quantum dots, then we have a problem. There are many types of semiconductor quantum dots. Some of them, actually many of them, can be toxic. So that's a problem. And then we have green technologies. Remember our good old friends, carbon dots? We talk a lot about carbon dots in this course. Carbon dots actually, if you design them correctly, they can do also the same job like semiconductor quantum dots. Because some carbon dots, if you make the surface in a special way, they can also have energy levels that will be good for using sunlight to excite electrons from lower level to higher level. And then you have the same effect. And then you have what we call green solar cells. Why green? Because carbon dots are not a problem. They're not toxic. They're made from natural sources, from sugar, for example, or from plants, or from organic waste. So that way you actually solve two problems. You use organic waste to make carbon dots that then can be put in solar cells. Now it will take time for this technology to be commercial. There are many challenges here of efficiency, of stability, but this is a very promising direction that people pursue for making solar cells. And that's it. Thank you.
Yeah, so thank you, Professor Raj, for a very nice lecture on the solar energy. So now, any questions for the students first? Okay, I'm having one question.
Sure.
So, what is your comment regarding the stability of quantum dots for the application of solar?
The stability is actually a very important thing because semiconductor quantum dots are fairly stable, quite stable. However, like everything in life, it doesn't last forever. And this is actually the problem of environmental toxicity. Because if you take quantum dots that have bad elements, like cadmium, like arsenic, like gallium, and other elements, over time, they might break and get released to the environment. And this is very bad. This is actually why still semiconductor quantum dots are not very popular in solar cell technology.
But it is comparable with the silicon
In terms of energy, it is, yes.
stability.
In terms of stability, I think it's less stable, yes.
Please go to the next slide, sir. Yeah, here in this green solar energy, you talked about quantum dot, isn't it?
Yeah,
The second figure,
this.
yeah, one,
This is carbon quantum dot.
carbon quantum dot. And could you put some more light on how that those red dots, are they the nitrogen doped?
Yes. The secret of making carbon dots good for solar cells is that you have to tune the energy levels that they will be good for light. So in order to make the levels between the low level and the high level in carbon dots can be tuned. Remember, when we talked about carbon dots, the colors, the different colors of the carbon dot depend on the surface of the carbon dot. So if you put different atoms on the surface, you can change the energy level. And this is the key challenge to make carbon dots good for solar cells. You have to work on the surface, to change the surface, to dope it with nitrogen or sulfur or various different atoms in order to tune the energy.
Thank you.
Very nice. Answers are just waiting for you regarding electrolyte in this green solar energy. What kind of electrolyte we use?
Very good question. There are many types of electrolytes that people use. Sometimes they are solid electrolyte, sometimes they're liquid electrolyte. Basically, the electrolyte that you use does not depend on the medium that you put here for a electron transfer. So some people use ammonium chloride as electrolyte. Some people use sodium chloride as electrolyte. There are various types of electrolytes, which is unrelated to if you use carbon dots or semiconductor quantum dots or silicon atoms.
Sir, nice lecture. Thank you. Wonderful. This might be a stupid question. What is source?
No question is stupid. All questions are good.
What would be the source for nitrogen doping?
It's actually quite easy. Remember the previous lecture when we make the guanidinium carbon dots? If you use a precursor with nitrogen, you'll have nitrogen there on the surface. So you can use amines as your starting material for making carbon dots, then you're going to have nitrogen on the surface. You can use free nitrogen, it's okay, but it's more difficult because when you start with nitrogen in your reaction, nitrogen is going to sit there covalently attached. If you take external nitrogen, you make carbon dots, let's say, and then you put them in a solution of ammonia, for example, or you bombard them with ammonia vapor, the nitrogen will attach to the surface, but physically. So it's going to be less strong, less stable coupling. So usually when you want to dope carbon dots or put some atoms on the surface, it's better that you put in your reaction the source of these elements, like compounds.
How much is the efficiency of the reaction here?
Again,
Efficiency.
it's quite efficient. To dope with nitrogen is very efficient, actually.
My question is, you told that we can actually tune the energy gap. Like semiconductor, we have very small energy gap, like 1 to 3 milli electron volt. So in quantum dot, how we can control the energy gap by controlling the size?
You mean here?
Here and also other quantum dots we have shown.
Well,
Symmetric quantum dots.
in semiconductor quantum dots, the size determines the energy gap. In the carbon dots, the surface properties determine the band gap. That's the big difference between semiconductor quantum dots and carbon dots.
How surface is effective for the carbon dot? Suppose here in this case.
That's the thing. It's very effective because the mechanism for determining the energy levels is the surface units, the surface residues. That's what happens with the carbon dots. If you have certain atoms, you have different energy levels. That's how you can tune the band gap with carbon dots.
Also, this dots, quantum dots. So what is the medium or like state? Like inside two electrodes, you're using a material. So how will it solid state? It is colloidal state or how will it?
Usually you make it in solid state. What people do, they take the carbon dots and they make it in a polymer matrix or in a gel. That keeps them very stable and still allows electrons to go out and go between the two electrodes. So it is basically a solid phase system, which makes the solar cell much more stable.
Any other question?
Just for curiosity, what will happen after using such material for a long period? Then it is going to dispose to the environment. Then it will create the same problem to the environment or less hazardous or
Actually, in this system, much less of a problem because here you just have carbon. So you take this, you throw it out, nothing happened. The world is full of carbon. It's not some metals, it's not some semiconductor materials. These are natural carbon atoms.
because these are the particles. The particle may rise.
You're right. Nanoparticles can be a problem, but still, most research on carbon dots find that they're not toxic, or they're much less toxic than semiconductor materials, because they're just made of natural sources from carbon.
So have they invented such devices or this is like proposed?
Yeah, no. These devices exist. There are papers of solar cells from carbon dots. They have problems. They're not so efficient as other silicon solar cells, but they're quite good.
How at economic level?
Economic level, they're cheaper because they're just made of carbon, but they don't generate so much electricity yet, and they're not so stable as silicon yet. So these are the challenges that maybe the students here can solve one day, and then we can have good alternatives for silicon.
We can take one or two questions from the students, right? Is it direct?
Somebody is interested. Otherwise, we can continue the discussion in the second half of the day. And it's now lunch break. So please join me in thanking Professor Raj for delivering nice lecture. And
This is not good.
We will be gathered here by 2 o'clock.
I feel that I need to,
Thank you.
so maybe I'll speak. If you don't fix
Hello. Hello. Okay.
Yes. Sure.
For
Yeah, yeah.
welcoming. Hello. So, good afternoon to all the participants, students, and faculty members. So, I thanks organizing committee, okay, for giving me this opportunity to introduce Professor Raj. So now everyone in the hall is quite familiar and friendly with Professor Raj. So everybody knows him very well, and while I observe the students interacting a lot with him, so he's really enjoying. So I urge all the students to interact as much you can and ask questions if you have any query. So he will be more than happy to answer all your questions, all your queries. Right? So Professor Raj, so far I think he has covered all the big spectrum of the nanotechnology, nanomaterials and their applications, mainly in agriculture, okay, in solar system, in water related system, how to get drinking water from the ocean, from the sea, and how to use nanomaterials in oil spill treatment. And yesterday he really pointed out how to get good publication and which are the major components that to be incorporated in a research article. Right? So I urge you again and again to interact with him. Right? So he didn't need any formal introduction. Now we have again the same speaker. So I welcome you, sir, again to continue on the same topic.
Yeah.
Thank you.
Thank you. Yeah, please, I'm here for you. You know, I'm going to be here until Friday. If you want to ask me questions formally or informally, no problem. Please feel free. I'm at your service. So we talked about many things. This topic actually is also huge. All this subject of energy storage is naturally a very, very broad field with lots of activity. Nanotechnology is part of it, but obviously we cannot cover it even in 1 year, not in 1 year maybe, but not in 1 hour. But we will try. I'll give some highlights, some stories where nanotechnology can help us in energy storage. So specifically, we will talk about batteries and supercapacitors. These are the two main features or main components of energy storage devices. So we'll talk a little bit about the differences and the common things about batteries and supercapacitors. Then we'll give some specific examples of how nanotechnology can help us with lithium-ion batteries, which are the most common batteries that people use these days. Then we will talk about nanoparticles in electrodes, which are the main parts of the batteries. Then we'll switch to supercapacitors, and we will talk about nanotechnology in supercapacitors, specifically in electrodes, how we're going to make good electrodes for supercapacitors. And finally, I'll tell you another story about something that we done in my laboratory about very interesting light-induced or photo-rechargeable supercapacitors. Now, why do we need energy storage at all? We talked before lunch on solar cells. Now, when we have solar cells and we have energy, we need the energy not necessarily in the same moment. For example, we have sun during the day. What about the night? We need energy during the night. That's why we need energy storage. We need efficient ways to take the energy from solar cells, for example, and store it for later use, for example, at night or in other times. This is why energy storage is at least as important as solar cells for developing new energy solutions for the world. Okay, it's not working, so I will. Okay, batteries versus supercapacitors. These are two main topics of energy storage. Each one is doing different functions. Batteries are naturally maybe the more important or the more widely used energy storage. What we have in battery, we have two electrodes, negative electrode, thank you, negative electrode and positive electrode. And all what we need to do, we need to have charges in the different electrode. We need negative charges in the positive electrode. We need positive charges in the negative electrodes. If we can hold the charges, we can separate the charges and hold them. That's how we store energy. When we need the energy, we're going to connect the circuit, and the charges will go away. Electrons actually will go from this side to this side, and we have energy, we have voltage. That's how batteries work. The concept is very easy, very simple. Of course, the concept is simple. Doing it sometimes is very challenging. This is batteries. Supercapacitors are working on the same concept, but their role is different. Again, in supercapacitor, we have two electrodes, negative electrode and positive electrode. In both electrodes, we have positive charge in the negative electrode, negative charge in the positive negative charge in the positive electrode. Now, the difference between batteries and supercapacitor is that when we operate the battery, the charges are actually moving from side to side. So the process is quick, and you can have many charges on both electrodes. That's why in energy, you can store a lot of, in battery, you can store a lot of energy. Now, in supercapacitor, what you have are redox reaction, reduction, oxidation reactions in both electrodes. This is why the amount of charge you can store in supercapacitors is lower, but because redox reactions are very fast, you can get very high power in supercapacitors. You can very quickly get a lot of energy. So basically, the main difference between batteries and supercapacitors are the energy. Batteries can store more energy. That's why in all our computer and cell phone, everything, we have batteries, because we want to store as much energy as possible. Supercapacitor cannot store so much energy, but they can give you very high power. They can give you a pulse of energy very quickly. In some applications, it's very important. If you want high energy in short time, for example, when you want to have electrical car and you need a lot of energy to get the engine going, that's why you need a supercapacitor. But supercapacitors cannot store a lot of energy. Anyway, these two systems, they complement each other. We need good batteries for certain applications. We need good supercapacitors for other applications. So let's start with batteries. And let's start with the most common battery that we use in the world these days. It's called the lithium-ion battery. Now, lithium-ion battery, as you see from the name, what we need, what we use for charging are lithium ions. Why lithium ions, do you know? Where is lithium in the periodic table? In the beginning, very, very small. It is actually the smallest ion that exists. Lithium has 3 protons, very small ions. Why it's important to have a small ion? Because 2 things. If we have small ions, we can store many, many ions in the electrodes. Small ions, certain volume, we can have many ions. If we can have many ions, we can store a lot of energy, a lot of charge. That's one reason why we like or we want lithium ions. The other reason, because lithium ions are so small, they can move very easily between the cathode and the anode. If they move very easily, it means that we can use the battery very efficiently. We charge the battery efficiently. We use the energy very efficiently because we can use the energy only if the ions will move freely between the 2 electrodes. So this is the main thing about lithium-ion batteries. The challenge in lithium-ion batteries, actually in any battery, is to design the electrode matrix that will be both good at holding the ions. You cannot just have ions going in solution and stick to the electrode. That's not going to be efficient. So we need a good framework for the ions to sit. And we also need the electrode to let the lithium ion move quickly when we connect the electrical circuit. And this is where nanotechnology is very important. Because the contribution of nanotechnology to lithium-ion batteries and other types of batteries is to design good electrodes with good structure, with nanostructures that will keep the lithium ions and let the lithium ions move freely. Okay? Let me just show you, actually, this is related to the previous slide about the difference between supercapacitors and batteries, so let's skip it. Just to summarize the difference between batteries, high energy, batteries, high energy, low power, supercapacitors, low energy, high power. So this is the essential battery module. Let's see how nanomaterials can help us in batteries. Again, we said we want good organization of the electrode, of the nanostructures in the electrodes that will give us good matrix, good electrode. What you see here in the scheme is actually one of the most popular applications of nanomaterials in lithium-ion batteries. What we see here are nanotubes or nanowires that are mixed together, forming the cathode. Now, these nanostructures are very important for several reasons. One thing is, when we have these nanowires or nanotubes in the cathode, we can have many sites for the lithium ions to sit. They can attach to the nanowires and have a stable organization in the cathode. The other thing about these nanowires is that you see there's a lot of empty spaces. There's a lot of pores. Now, why do we need these pores? When we connect the circuit, the lithium ions need to go away and come back to the anode. So we need all these open spaces for mobility of the lithium ions. These are some examples of lithium-ion batteries using nanostructures. In the cathode, we have certain crystalline structures. They can be from many materials. Some popular materials, some nanostructures in the cathodes are polymers or transition metal oxides. Again, all these species are very important in terms of sites, keeping the sites for the lithium and letting the lithium move back and forth. Now, in the anode, you need different organization. You need an organization that will be both porous, but you need it to be also conductive. You need to have electrons going from the lithium metal to the electrode and closing the circuit. This is something you don't need in the cathode. In the cathode, you just need a nanostructure to have sites for the lithium ions to sit. But you don't care about conductivity. The electrons for the lithium will come from here to the electrode. So one thing about nanostructures in the anode is they need to be conductive. Now, there is a very good material that can be conductive. You know what it is? It's written there. Carbon. Carbon, which we talked about a lot, is both good for us, but it's also conductive if you make it in the right way. Remember yesterday we talked about graphene. The graphene sheets, they are excellent conductors. There are other, graphite is also very good conductor. So in the anode, in many batteries, we have organization of carbon nanostructures, again, that will give us a lot of surface area, also conductivity. Here we just have, there's thousands examples in papers about nanostructures in lithium-ion batteries. Okay? People are always trying to make new materials, improving the energy density, improving the conductivity. This is a very, very active field because lithium-ion batteries are so important. So here you see some example. People made this composite material in the cathode, lithium, iron, phosphate. And then in the anode, we have these carbon structures. Again, many, many different designs. But what I hope I showed you is what is the purpose of these designs, these nanostructure designs in lithium ion batteries. Okay? And again, we talked about graphene. Graphene is very good and very important in lithium ion batteries. I think actually there are commercial lithium ion batteries with graphene. Now, you can have also nanoparticles as part of the battery electrodes. This is just an example of an interesting cathode material made of tin dioxide nanoparticles. Okay? So they show you here how they make the electrode. They start with some big particle. They do some chemical process. But what is important is this. It's interconnected tin oxide nanoparticles. Again, why we like it? It gives us a lot of surface area, so we can put the lithium ions in many places inside the electrode. It also gives us these spaces here, which gives mobility to the lithium ions. So this is nice electrode. This is the battery world. Again, what I gave you is very little insight about nanotechnologies in batteries. There are thousands of examples of nanostructures and nanotechnologies in the battery research. If any of you would like to work on that, obviously you need to search in the literature because it's extremely active field. So, we talked about battery. Let's talk about supercapacitors. Remember, supercapacitors, more power, less energy. This is just an example of the concept of supercapacitor operation. Again, we have two electrodes. We have the charges inside the capacitor, just moving around. When we charge the supercapacitor, when we connect it, we see that the charges go on both sides. They are organized. Negative charges on the cathode, positive charges on the anode. That's when the supercapacitor is charged. Then we want to use the supercapacitor, so we connect it through a load, and the supercapacitor can give us energy very quickly. Okay, and the electrolyte or the charges going back to the electrolyte. Actually, when we look closely on the supercapacitor component, again, it's very simple electrochemistry. This is the cathode, the positive electrode. This is the negative electrode, the anode. And in the middle, you have the electrolytes. Now, the electrolyte is very important because the electrolyte are the charges that go between the electrode and give us energy and give us power. Now, in this picture here, you see the most important part of the supercapacitor and why we need nanotechnology. If you look at the electrodes, they're very porous. We need a lot of surface area in the supercapacitor because what will determine the power and the effectiveness of supercapacitor is how many charges you can put on the two electrodes. if you can put a lot of charges, you can have high power. That's what's important about supercapacitors. So the requirement in the supercapacitor world is to have high number, high concentrations of charges on the cathode and on the anode. If you have a porous electrode, then you can put a lot of ions because you have very high surface area. So if you need porous electrodes, nanotechnology can really help you, because nanostructures can give you a lot of surface area. Actually, there are two types of supercapacitors. Both of them require very high surface area. One mechanism of supercapacitors is just accumulating charges on the anode and the cathode. Again, we need a high surface area for the charges to accumulate. Another very interesting mechanism in supercapacitors is called pseudocapacitance, and we have redox reactions on both electrodes. Again, in both cases, we need high surface area. So also in the supercapacitor world, if you open papers, there are thousands of papers of people making very intelligent designs for the electrodes that will give us high porosity and high surface area. Here just few examples. Some people put just activated carbon, regular surface area. Other people put holes. You can have holes in the anode and the cathode. By putting holes, you can have the charges accumulate on both sides of the electrodes. The sizes of the holes are nanostructured, nanoscales, to let only ions go in and out. And then, of course, you have various designs of nanostructures to give us high surface area. Again, you have beautiful studies, beautiful pictures. You can see here just an example of some composite material from nickel, cobalt, carbon, whatever. You can build nano towers. You have nano channels, nano sheets, nano cones, everything nano, as long as you give very good surface area for the charge to be stored. Now let me finish with a story, an interesting story about photo-rechargeable supercapacitors. Basically what we're trying to do here, we were trying to make a supercapacitor that we can charge with light. Now why do we want to charge supercapacitor with light? Why is it good for us? Ideas. Is light good, bad, cheap, expensive? How cheap? Does light cost us money? Environmental, that's right. How much light cost us? $0, 0 rupees. Why? Go outside, the sun is free, it's still free. Maybe the government will charge us for the sun, but light is free. So if we make supercapacitor or a battery or whatever, we put it on the roof, okay? And then there's sun, there's light coming, and we can charge the supercapacitor with the sun. This is going to be great. It's not going to cost us anything to charge the supercapacitor. You know, if you have a cell phone or computer or whatever, You need to put it in electricity, you need to charge it, it costs you money, okay? It's not such a high cost. But think about a giant supercapacitor that you want to have air conditioned for this entire building. It takes a lot of energy. So if you have some supercapacitor or a battery that can be charged with light, with the sun, that's going to be extremely useful. So that's the idea, to make a photo rechargeable, light rechargeable supercapacitor. Now, things like that already exist. People made photo rechargeable supercapacitors. The way they make them usually, there are two ways. You can make a supercapacitor that the electrodes will be light sensitive. So when you shine light on the electrode, you're going to have some chemical reaction that will give us the space, the charging of the ions. This is okay, but it's very difficult. It's very difficult to make electrodes. It's chemically difficult to make electrodes that will have some chemical reactions that are triggered by light. This is why these things, you don't find them in the store. They're not practical because it's difficult to make. In our system, we use a different concept. What we used are electrolytes that are going to be light sensitive. So instead of making a very complicated electrode with complicated chemistry that's going to be charged by light, we'll do something totally different. We will make electrolytes that are going to be charged by light. And for now, you know that I really like carbon dots. So the electrolyte that we used are carbon dots. And let's see how it works. You saw this picture 10 times already. One reason why we like carbon dots, because it's very cheap, etc., etc. We can make it very easily. We don't need to be a sophisticated chemist to do that. We saw this one also, the color properties of carbon dots, and we saw this also already. This is also going to play a role in this system that I will describe to you now. Specifically, this, the photothermal effect of carbon dots. How does it work? This is our photo rechargeable supercapacitor. What we have, two electrodes, standard electrodes, nothing complicated. You know, in every supercapacitor you need to have electrode. Here, this is the electrolyte. Now the electrolyte that we used are carbon dots. But the carbon dots in this case are sitting inside a polymer. So it's a solid material, a polymer called polynipam. Now, polynipam, this is just the electrode. It's a standard electrode that we make with nickel and ruthenium. And the electrolyte, the carbon dots sitting in this polymer called polynipam. Now, polynipam is a very interesting polymer. It is a heat-sensitive or temperature-sensitive polymer. And what I mean by that, in low temperature, the polymer chains are extended and the polymer is hydrophilic. The surface here is hydrophilic it attracts water. Above a certain temperature, which is actually about 32 degrees, the polymer changes its phase. It undergoes a phase transition, and these chains are getting entangled, and the polymer becomes hydrophobic. So we have a hydrophobic phase transition induced by temperature. What does it have to do with supercapacitors and carbon dots and all this story? This is the interesting part. In high temperature, the polymer, in low temperature. In low temperature, the polymer is hydrophilic. Now, if we put inside the polymer carbon dots, hydrophilic carbon dots, charged carbon dots, in low temperature, the polymer is hydrophilic, so the carbon dots will sit on the polymer. They'll stick to the polymer because the carbon dots are also hydrophilic, they are charged. Now, when we shine light, what will happen to the carbon dots? You should know this by now. They generate heat. The photothermal effect of the carbon dots. The carbon dots going to absorb light, release heat. They will release heat to the environment. What will happen to the polymer? The temperature of the polymer will go higher and higher until the polymer will do a phase transition. The polymer will become hydrophobic. Now, if the polymer becomes hydrophobic, what will happen to the carbon dots? The carbon dots initially here, they sit on the polymer. But at higher temperature, we have hydrophobic polymer. The carbon dots don't feel good anymore. They cannot attach to the polymer. The polymer is hydrophobic. The carbon dots are hydrophilic. They are charged. So the polymer will need to go to the solution. They will have to leave the comfortable home of the polymer. If the carbon dots are in the solution, they will be an excellent electrolyte for the supercapacitor. And then the carbon dots can give us energy. The carbon dots can be used to charge the supercapacitor. And this is the concept that we have here. In the dark, at night, the polymer is hydrophilic, the carbon dots sitting here, nothing happened. No electrolyte in the supercapacitor. The supercapacitor cannot charge, cannot give us energy. Nothing happens. But when we shine light on the supercapacitor, when there's sun shining, then the carbon dots absorb light, release heat. Release heat, the temperature of the polymer goes up. The carbon dots get released. They can go anywhere they like, and we have an electrolyte to give us energy. This is the concept, just to show you that it really works. See, this is the simple test tube, plastic tube. Okay, we put two electrodes here. Here, this is the polymer without carbon dots. Here, we see the polymer with carbon dots. Carbon dots are brown, so we see a brown color. Now, we shine light. Initially, nothing happens. 2 minutes, the temperature goes up. And you see that the polymer becomes kind of cloudy because the polymer becomes hydrophobic. We shine more light, 4 minutes, the temperature starts going up here, 26 degrees, more cloudy. 8 minutes, higher temperature. You see it's even more cloudy here. 34 degrees, at 10 minutes we get 34 degrees. And this is total phase transition. We even don't see the carbon dots because the polymer becomes like a gel, very cloudy. This is how we perform the experiments. Here you see the energy, the capacitance of the capacitor. So just by having carbon dots, we get a very high capacitance. And what you see here is a cycling. We can charge and discharge the capacitor many, many times just by shining light. Okay, so we shine light, high energy. We charge the capacitor. We turn off the light, low capacity, high, low, high, low. This supercapacitor can be used 1,000 times just by shining light. And just to show you that this is actually working, see, first we shine light, we charge the supercapacitor, and now we disconnect it, okay? No, we don't, we connect it to the lamp here. You see an LED. Let's see. It's working. We charge the lamp just by the supercapacitor. And it will go for a few minutes, which is what we want from energy storage. So science works sometime. Let's see it again. Oops, sorry. Shining light, these are the supercapacitors. We shine light, so we charge the supercapacitor. After shining light for 10 minutes, we connect the lamp to the supercapacitor. So this is going to be our power source, just like a computer or a cell phone. And our supercapacitor charges or uses its energy to light emitting diode. So it's not commercial yet, of course, but it's a nice concept. And maybe one day we can have supercapacitors on a roof that are containing carbon dots, and they will be induced by light, and I will be very rich, maybe. Thank you. We need to charge them.
When we increase the concentration of carbon dioxide, then the efficiency will increase. But sir, you have that shown the graph that's showing that when we increase to two decreasing that one.
First of all, I think you are a very good observation. it means that you really listen to the lecture, which is very good. That's true. When we look at this graph, we see 0, it's not so good. Then half milligram better, 1 milligram is better, 2 milligram is not so good. You know why? Because when you have so many carbon dots, it's getting crowded. Just like people in a crowded room. If you have too many carbon dots, it's very hard for them to move, and then they're not good electrolytes. That's the reason why you don't want too many carbon dots. You need enough carbon dots to be able to move freely from the anode to the cathode.
First of all, sir, thank you for the tailored discussion. So my question is that not related to the concept, but these concepts are so amazing. My question is that you have thought about all these, or you have a team along with you, sir? Because when you said let us make the electrolytes move, and that is like a very nice concept. So, sir, this is your thought process, or?
That's a very hard question. You know, I like science. I like other things in life. But usually I think of my projects. And the way it works is that you start with something, and if you think and think and think, sometimes you have interesting ideas. This idea came because we have been working for maybe 5 or more years on supercapacitors. And we worked a lot on electrodes of supercapacitors. We made different nano porous electrodes. So we had a lot of work on supercapacitors. Now, because we worked so many years on electrocapacitors, then I was thinking, okay, we have electrodes, but we also have electrolyte. What can we do with the electrolyte? And then of course, you see that we did a lot of work with carbon dots. So we did 1 + 1, the photothermal effect of carbon dots, this story about supercapacitors, and then the idea came. You know, some ideas don't work. It's not everything that is working. But sometimes things work. If they give you money to do these experiments, then you can do many things.
Thank you, sir, for your nice and very interesting lecture and the topic you have covered. One of my queries that I have heard mostly the liquid electrolytes, right? But is there something like solid electrolytes?
Actually, for practical applications, people like solid electrolytes better, because liquid electrolyte, you know, if you have some cracks, it can go leak. So the field is actually moving to solid electrolytes. Even in solid electrolyte, you can have mobility. It's more challenging, but it is okay. It's practical. This specific system that you saw, it's actually more solid electrolyte than yes. It's not completely solid, it's like a gel-like. Yes. You know, it's not so efficient in terms of energy density and power density. But the nice thing is the concept. And you know, 100 years ago, cars were very slow and very inefficient. Then there's engineering to make it better. Hopefully, this concept will go towards better engineering. Yes, we are working on different, yeah, not the same thing, but other similar concepts.
Where you have taken
Not rubidium, ruthenium. This is just, I told answer her that we've been working on supercapacitors for several years. And actually this ruthenium oxide electrode is some porous, very efficient porous electrode that we developed before, like 3 or 4 years ago. So basically we use the same electrode in this system. But this is not the important part. The important part here is the electrolyte. But we used a very good electrode in order to give us good power properties and energy properties.
Any question from benchers? No. Okay. Sir, one of the pictures you have shown that polypeptide.
So thank you for the interesting insight. So my question is, there are various synthesis methods for this. So what have been used in your work? What synthesis have you used for the carbon dots?
For the carbon dots, it's not, we can use any synthesis we want.
So what have you used to obtain carbon dots?
In this case here, it's citric acid. Citric acid and ethylamine, I think. The important thing for us is to make carbon dot that will be hydrophilic. So to make them, if you remember before the lunch break, I described carbon dots from citric acid and from guanidinium. And this makes them very positive. So we use the same thing, similar thing here. Citric acid and some amines. I think it was ethylene diamine that gives us carbon dots that will be positively charged.
So you also talked about the matrices for that electrode and electrons. So how do we know about the matrix structure?
Well, you can take something that other people made, or you could do something that you made. Now, the same thing that he was asking, we used in here a electrode of ruthenium oxide, okay? We used oh no, where is it? Here. We used a nickel ruthenium oxide. This is actually a very interesting electrode. You see, it has these trees, nano trees. We synthesize it in our lab, and this is a very good electrode because it gives you a very high surface area. Remember, I said it's important to have high surface area. So we have this electrode that we used from our development. But you can use in this system any electrode you like.
Good afternoon, sir. So my question is that all the polymers are not hydrophilic at low temperature. So what will happen if we take the hydrophobic polymer?
This is a very good question. You cannot take any polymer. The unique thing about this system is the polynipam polymer, which has hydrophilic phase in low temperature and hydrophobic phase in high temperature, and the transition temperature is 34 degrees. So it's really a very special system for this polymer. You cannot take any type of polymer for this application. Maybe you can find other polymers that do the same thing. Then it will be wonderful.
Regarding the same picture, at low temperature, the polymer is hydrophilic.
That's right. Yes. Well, the functionality is just the hydrophilic or hydrophobic. There's no other changes. Actually, that's what's interesting about this polymer. Because when you increase the temperature, these rings, these polymer chains, they start moving very fast until they collapse and they make this hydrophobic phase. Exactly. In there? No, there's no change. It's the same polymer. Yes, it's a structural change. Okay. Sure. If it, no, it will work definitely, but the question is, how do you heat it? You can do this with carbon dots. You cannot do it with any type of nanoparticles. The nice thing about carbon dots is that when they absorb light, they release heat. Actually, there are other types of nanoparticles that do similar things, like gold, for example. Gold nanoparticle also absorb light in certain wavelength and release heat. So actually, you can try this with gold nanoparticles. I don't know. You have to check. Exactly. Yeah. You should do it. It's very interesting. Yep. Mm-hmm. Yeah. Sure. So sounds beautiful. You should try it.
Thank you very much for that very insightful talk. So just one curiosity, did you investigate the effect of pH on the binding and detachment of this carbon dot to the polymer? Because the beta potential of carbon dot is highly dependent on the pH of the solution. Right?
That's right. Part of the optimization of the system was actually selecting the correct pH or selecting the pH that will give you the best results. So absolutely you're right. The pH has a strong effect on the surface charge of the carbon dots and how they are behaving in the system.
We have to maintain that pH. It should be a buffer.
Yeah, and we can do it with buffer, sure.
Thank you.
Anyone else? No. Okay. Thank you so much, sir, for giving an insight.
Sure. want a sensor, the basic concept is very easy, very simple. This is the concept of electrically based sensors. You can use electrical resistance, you can use electrical conductivity, you can use electrical capacitance, all these different aspects of electricity that you can use as the mechanism for sensing. Now, in all these systems, the concept, as I said, is extremely simple. You have an electrode and you have another electrode. Between the electrode, you have current. You have electrons that are moving in a current, in an electrical circuit. The unique thing about every sensor is what you have here. This is the chemistry. This is the nanotechnology. Here is the sensing material. And if you make the sensing materials very innovative and interesting and efficient and sensitive, then you can make a good sensor. So the sensing material, basically what it needs to do, it needs to absorb the pollutants from the air and tell you that there are pollutants. So for example, if you want to develop a sensor for carbon dioxide, for example, so again, you have the two electrodes connected through some kind of resistance meter, and then you have here the medium, which is the place where you can do your inventions and innovation. For example, you can put a nanomaterial layer that will absorb very well carbon dioxide molecule. In this case, this is your target. If you absorb the carbon dioxide molecules to your medium, it will change the properties of this medium, and you're going to have a change of the resistance. Okay? So all the story happens here, in the place where you absorb the gas molecules, the pollutant molecules, the nanoparticles, whatever is your target for detection. And if you absorb them well, if you have good sensitivity to the nanomaterial that you use, you're going to have a good sensor. So what I'm going to show you now, just few examples of sensors based on nanomaterials and nanoparticles. So this is an example of again, a simple sensor in which the sensing area is made of a thin layer of nanomaterial or nanoparticles. We have lots of nanoparticles here from different compositions. And what these nanomaterials, nanoparticles need to do, they just need to have an affinity. They have to absorb, to bind the gas molecule. So the properties that you need for these nanoparticles are good interactions, good affinity with gas molecules. Now again, why nanoparticles are good for you? Because nanoparticles can give you a very good surface area, very high surface area. You want high surface area because you want to absorb your gas molecules. The more surface area, innovation or the activity is designing the film, designing the surface in order for it to absorb efficiently the gas molecules that you need. So that was the general description of a nanoparticles and nanotechnology for gas sensing. Now let me tell you about our work in the lab, in which we used an electronic nose based on carbon dots for smelling bacteria. Okay? The objective here is to be able to detect bacteria, to sense bacteria using the gas phase. Now, why is it important? In many cases, we have bacterial infections in various foods. These are just some articles from newspapers where you read that people go to the supermarket, they buy some food, the food is contaminated with bacteria, they eat the food and they can get very sick. This happens a lot of times. Now, in most cases, of course, there should be some regulation that there will not be bacteria in food, but in some cases there are contaminations of food with bacteria. So you want to develop a way to detect bacteria very efficiently and very quickly, for example, in food. If you will have a sensor that will be cheap, sensitive, easily applicable for bacteria in food, you can save lives, you can help people not getting sick, and of course you can open a business and sell it. There's also bacterial infection in hospitals. You know, in hospital it's very dangerous to have bacteria when people are sick because they can get even more sick. So again, even in hospitals, in the walls of the hospitals, on tables, in instruments, surgery, you want to be able to detect bacteria quickly and efficiently. And surprisingly, there's not too many ways right now to do quick detection of bacteria. How do you diagnose bacteria? Usually what people do in hospitals, in labs for testing food, what they do, they take a sample, they put it on an agar plate, and they grow the bacteria. It takes 24 hours, it takes 48 hours. It takes a long time until, if there are bacteria, you can see them growing here. Sometimes you can see it through the colors that they make in certain dyes. But all these techniques are very slow. It takes long time. And usually you do it in the lab. So it's complicated. You cannot take every meat or every vegetable that you buy in the supermarket and send it to a lab and they can tell you there are bacteria or there's no bacteria. It's very inefficient. So if you can come up, if you can invent a very simple sensor for bacteria, it's going to be really useful. And that's really our objective. Our objective is to develop sensors that will be easy to use, that will be cheap, that will be efficient, that will be quick for detection of bacteria. Now, the nice thing about our approach Probably you can also. Anything that we bind will change the capacitance. That's the concept. So anything in the air might change the capacitance. Yeah. Your nose can smell everything. If your nose can smell everything, this is. Yeah. Of course.
Hello, hello, hello.
around the metal layer battery. So you just remember two terms. One is the oxygen reduction reaction, ORR in short, where typically what happens, oxygen gets reduced with the help of some catalyst to the water is mainly, but here it is written as like hydroxide ion. So oxygen gets reduced, and in as a counter reaction, you know, once it is redox reaction is happening, then one is oxidation and another is the reduction. So if oxygen is getting reduced, then the other side metal, basically here like zinc, is getting the reduction, oxidation. So this is a combined oxidation reduction process, but driven by the oxygen partners. And at the same time, in the anode, which is oxygen evolution reaction, in short it is OER, where the water molecule basically get oxidized and results oxygen evolution, which ultimately release the 4 electron. Now the important point is that when the reduction reactions happens, oxygen reduction, as you know or you might have experienced, that once you do the reduction reaction, it release the energy, right? So in the battery point of view, just I am correlating, in the battery point of view, once the reduction reaction happening, it release the energy, or you can say you can utilize that energy. And when oxygen evolution reaction happens, it basically works for the charging the battery. Okay, so uh, in the primary batteries, so what your batteries you are using, I'm using here pencil cell even in this, what your battery you are using in your day-to-day life, which you cannot recharge it further, that categorized under the primary batteries. And the other one, which you can basically further recharge it and reuse it and keep doing the same thing, that comes under the secondary battery category. Again, in the primary battery, the main function happens at the reduction, not oxygen, but some sort of reduction. So if you just take example of, let's say, pencil cell, then there you find like zinc will be oxidizing to the zinc oxide, and manganese oxide getting reduced at the other end, and you get the energy. And that is not since rechargeable, so you need to use it. Once you find the electrolyte ammonium chloride, mainly when it becomes black, you need to just throw it out, right? But if you see the other part where the it can be recharged, then along with the reduction reaction, oxidation reaction is equally important and efficient. So once the battery get discharged as the results of reduction reaction, then at the second end it start oxidation reaction, again oxygen evolution reaction in terms of metal layer battery, then it gets recharged. So you can keep on using those batteries. Okay, so this is just a basic principle for the rechargeable metal layer batteries. And since oxygen is abundant, so this has really a potential to change the energy landscape if it can be properly addressed and utilized. Because having such catalyst which can work in terms of stability, in terms of efficiency, in terms of non-hazardous nature, if can perform both the function or individually, then it can really solve a big problem related to the renewable energy. So there are a couple of reports where people are claiming to use such batteries for different purposes, especially in vehicle. So you can find it all around in the internet. But the important point is that particularly why the zinc air battery becomes much more important, because of course zinc is abundant, especially if you see geographical region, then India is the fourth largest producer of the zinc, okay, worldwide, and it is safe, it is much cheaper. So this really attracts a lot. Now I will just
focus a little bit on the basic design of the molecule in order to get the property which can perform oxidation reduction reaction as well as evolution reaction. So if you consider a conjugated microporous polymer, which basically name itself suggests, first term is the conjugate redox active. So redox active means you have to have two unit where one is act as electron donor, the other one can act as the electron acceptor, right? Then only you can get the redox active properties. The second thing is the conjugated. You all are chemists, so even physicists, so you can know better that it has a continuous conjugation, and then only it can help to flow the electron from one end to other end. Then the microporous. Now here you can consider this like a pore, okay? So which basically helps again to provide the high surface area, to facilitate the substrate diffusion inside the pores. So eventually you will be ending up a better efficiency as compared to the non-porous material. And the last but not least, one of the important parameter is the substitution at the organic linker. So since it is like a complete organic framework, so you must take solubility, stability in the account in order to design the framework. So for example, there are some framework or molecules which are excellent in property, but you cannot dissolve them or you cannot make the blend properly. So for example, like lot of fluorinated products. So you need to tune in such a way. So sorry. Okay, you need to tune the substitution in the organic linker in such a way so it can balance a very nice way to get the very good film or layer or whatever you are making, going to make. Now if you have taken these things into account, it can form like 2D layer kind of a structure, and since you have substitution, you have porosity, so ultimately you can expect a nice outcome. This I'll not talk because already Professor Zaz has told several times about semiconductor nature. So where basically you generate a whole pair where valence bond and conduction band. So basically the electron will be going from valence bond to conduction band, and that has to further flow rather than coming back in order to get the electricity. So this is again, considering the design principle, now I'll be just going through a proper investigation where how you can have a property of ORR and OER catalysis in a molecule or in a material which can perform both the reaction or both the activity. So as I mentioned, it should be redox active. And one of the very nice molecule for the redox activity is triphenylamine, which is having nitrogen in the center, and that can basically roam around basis on the need. So basically you have 3 amino group, and the lone pair of the central nitrogen is free to basically switch towards the those amines. And if you basically connect it with properly conjugated linkers, and now here if you see the difference, the one linker which is called as like a mix, that is having two alkyl chain. One side it is glycol, the other side is having the only alkyl chain. The other one having glycol chain both the sides. Now you will see just a small tuning in the side chain, how it basically results in the property. So this is the characterization things which you can leave. Only important point is that if you have a mixed side chain, that end up with kind of agglomerated or globular morphology, but the glycol chain in the one which is having both the side resulted in a very nice fiber kind of morphology. and you are continuously listening since morning that if you have a narrow wire kind of morphology, or which can basically provide you high surface area, that can enhance the property together. So just a small change is resulted the different morphology. Now once we perform the ORR reactions, we found that the mix one and if you compare the performance of mix one and the diglycol one, you can leave other things for time being, but you see the current density under the very similar condition. The one which is having the morphology or nanowire kind of morphology is giving better ORR reaction. So that means, again, the proof of a fundamental concept that if you have a large surface area by any means, you can get the better performance. It both has shown tested almost 12 hours, and which has shown a very good stability as well. So now we have a material which is ORR active. Just remember the core moiety of triphenylamine. Similarly, based on the literature, we found that getting ORR activity actually is much more difficult than the ORR. As compared to ORR, getting OER activity is much more difficult. Now, for the OER, based on the available literature, we found that if you take the cobalt, which is again redox active metal, this shows very good OER activity. But the only thing you have to have either cobalt, metallic cobalt or atomic cobalt, or even some nanoparticles. You cannot have simple salt of, let's say, cobalt hexachloride. Okay, so here we have taken phthalocyanine and we have encapsulated cobalt in the main core. The other moiety remains the similar. Morphology here we got almost layered one, but the important part is that we got OER activity from this material, which is having cobalt in the core. The OER is giving almost the current density of, let's say, 13 milliamps. Now, out of this, the most important, like Toffel slope, which is giving the information about the reaction kinetics. So it is having around 87. If you see the literature, then it is really found in very good place. So now we have two material. One is having basically cobalt base, the other one is having the triphenylamine base, and one is showing ORR, another is saying OER. Then we have another design where we tried to put in such a way so we can have both together. So in this one, using fluoroglossinol and again triphenylamine as a precursor, we got again a redox active polymer where you can see that fluoroglossinol is like electron acceptor and triphenylamine remains as a electron donor. Then, and as I was telling that this material itself is a ORR active, but not OER. However, if you dope the cobalt nanoparticle through whatever way you want, even if you have triphenylamine, you don't need to add any reducing agent. It works itself as a reducing agent and it forms the cobalt nanoparticles. Now, if you have cobalt nanoparticles on the other hand, it gives the activity for both. ORR driven through the triphenylamine and OER driven through the cobalt nanoparticles. And this is the data. So basically cobalt nanoparticle stabilize on the surface of triphenylamine. Okay, and you see the ORR and OER both are giving reasonably good, but I have not shown the data, but if you see the stability towards OER, then it remains moderate because these are the nanoparticles. Over a period of time or over a several cycles, it start leaching out, right? So maybe after 12 hours or 14 hours, you will find that the cobalt nanoparticles leaching out from the material and you are losing the activity for the OER. Then we thought, okay, let's have some more fun and try to coordinate the cobalt in the framework rather having the nanoparticles. So we have another OPE linker where we have chosen the pyridine derivatives. Now, once we form the polymer from both of them, it gives a imine kind of bonding, and also it gives opportunity to hold the metal ion as such. And indeed, this material has binding capability with the metal side. After all this characterization, which I am not going through, we found that using similar ways, this gives a cobalt coordinated framework, porous organic polymer. Now, we have seen through different analyses that this is having almost 2.5% of cobalt chloride, which is bounded through these two nitrogen. So forming basically 5-membered zinc kind of things. Okay. Then once we perform the activity first with bare polymer without the metal, it was giving the OER activity, you can see just only 3 milliamps current density. But once you have cobalt in the framework, coordinated cobalt more precisely, it gives almost 100 times better, or 10 times, sorry, 10 times better OER activity, okay? Now the current density is around 30. In previous cases, if you remember, it was maximum 12 or 13, okay? And even TOEFL slope was much better. Stability also for this one was excellent, okay? So we found a material which is having both the individual property of oxygen reduction as well as oxygen evolution in such a way, so it is stable now, it is having sufficient doping and nice performance of ORR and OER. Now, once we elucidated the mechanism, we found that for the ORR, only nitrogen of the triphenylamine is responsible. So we found that although cobalt is available, but the oxygen remains with the triphenylamine due to presence of the electron at the nitrogen center. And this is responsible for the oxygen reduction. However, for the OER, the water molecule goes to the cobalt center and it performs the OER. So it again proven that both the individual property important to perform the bifunctional activity. Using this, we have constructed the zinc air battery. I'm not the expert in battery particularly, but one of my colleague in the same lab has constructed, since we got the basic fundamental fulfilled for the battery. Then we have used zinc basically kind of sheet, okay, which works as a redox active and balance both the reaction as a counter reaction, okay. So one-sided, the same material, one-sided coated, where it performs the oxygen reduction reaction, the other side it is coated and it gives the oxygen evolution reaction. And in the middle, zinc layer remains as such to balance both the reactions for the both sides. Now, zinc air battery performances, open circuit potential was 1.35 and specific capacity was 837, which is comparable with the market available products. Important point is that if you see the charge discharge curve that was performed almost 18 hours, so basically one side it is charging, another side it is discharging, and that represents directly ORR and OER reactions. So if you see, although at the end of 18 hours the graph remains broader and it shows that now it is taking much more time compared to earlier, but still it is with the range of charging and discharging. For illustrating the practical application, I will tell you, we have constructed with I think 3 or 4 milligram of the product, this battery with all the jugaad technology, and we found that two LED, a small LED, was able to lit for 48 hours without further charging. And of course, it get discharged after 48 hours. You leave it for a few hours, you again start, it will again lit. So point is that since oxygen is available in plenty, it it is kind of self-rechargeable or self-driven or self-breathable battery, which doesn't need any extra charging from electricity support. You just leave it for some time. It will take the oxygen from air. It will keep doing the OER, and at the end of OER, you will get your battery get charged. Now you can use the electricity, it get discharged over a period of time, you again keep it for some time, it get charged. So that's the cycle works independent to the any energy source. So that was the overall picture. So summary, we started or I started here to show you a material having redox activity connected with the triphenylamine that was only ORR active. Then we have cobalt integrated in the material which was showing only OER. And the third one where we have both the property TPA, triphenylamine and cobalt but as a nanoparticle. It was active for ORR and OER but having low performance as well as poor stability. But in the fourth design where we have triphenylamine and cobalt is integrated as a coordinated form, atomic form in the framework, that was showing excellent performance and nice stability towards the zinc air battery, and we have successfully constructed that. So with this, I will acknowledge my postdoc supervisor, Professor Majhi, for great support, and he was the person behind all this study. And of course, funding agencies, UGC, SCRB, and a big thanks to all of you. Thank you.
Thank you very much, Ashish sir. Very nice and exciting work, lot of big pictures, lots of data, and you have done tremendous job.
Thank you.
So with that, is there any question? Yeah, please. Yeah.
Thank you for interesting talk. For just a general question about zinc air battery, so you need to maintain the oxygen level in this battery because oxygen is getting like released, isn't it? Or
So this was having a kind of breathable this film, which was basically taking care of releasing the oxygen after the OER,
okay,
oxygen evolution.
so do you need to keep the oxygen for
No,
the
no, no,
reduction?
no, no, no. It's only from air without giving the extra concentration of oxygen. It was working nicely. Yeah, thank you.
Sir, very nice one. So when you are just flying, how many times that can be recharged? So
So you mean the final battery setup or okay,
balancing battery.
okay. So at least we have done twice, thrice, but I mean we should check more often and more periodically. But even after twice, thrice means after a week time, we did not get any degradation in terms of the efficiency.
So immediately when the use is commercial, it won't be.
It is like a very basic level at this moment, but definitely if we can imagine like within the 3 milligram of the product we are able to lit 2 LEDs, then if we take let's say 100 means milligram or even more, we can think of a better application because we have at least done a small motor in the lab using the battery, this battery. So we had that much. Thank you.
Thank you, sir, for giving the very good and exciting lecture.
Thank you, sir.
So now we will have another lecture of battery cycles. Okay, so I quickly introduce Dr.
Thank you, Sarma sir, for the kind introduction. I welcome Professor Raj and guest for Dr. T.P. Binod sir and head sir. And thank you, students, for your kind presence. So today, I'm going to show from my some PhD work, which I've done in IISc. So here, the talk is going on nanotechnology. That means some materials at nanoscale. So I am going to talk on molecules, not materials. So molecules, can we make molecules of nanometer size? Normally it is smaller than the, like if you take one molecule, so that size will be in Armstrong or picometer range. So if we stitch the molecules, several molecules, so it also may form molecules of nanometer size, which is called supramolecule. So in my talk, I'll give some light on supramolecular self-assembled cage, self-assembly process I will explain. And next, I will go to some example of the supramolecule. So one example is metal barrel, like metal coordinated structures. And another next, I will go to some pure organic cages. That also you can prepare. So two example we'll show here. One is metal coordinated, another is pure organic. So what is supramolecule? If you check the structure, this is dodecahedron it is called. And it can be formed from combination of a pentagon, two-dimensional sheet. So it can form a dodecahedron. So on 2D structure, you can prepare a 3D structure with a definite shape and geometry. So our also approach is to prepare supramolecule. We'll start from small molecular unit. Maybe the size is 0.1, 0.2 nanometer, very small angstrom scale. And if we can get a supramolecule which may have 1 to 10 nanometer diameter range, if it is macromolecule, large molecules. And can we control for that? Because we know synthesizing molecule is not a easy task. So quite it is hard to synthesize large molecules. So now in this session, we'll see some examples how we can prepare a large molecules which have nanometer size diameter. So first of all, I must say about the Nobel Prize in 1987, where host guest chemistry was recognized by Cram, Lane and Peterson. They were awarded because they have shown the importance of macromolecules, which is called supramolecules, and their molecular pocket. For example, a crown ether, everybody knows the crown ether. It has a two-dimensional structure and oxygen atoms. So based on this size of the crown ether, it can selectively detect metal ion, can bind metal ion. For example, a 4-member ring, 4 oxygen member ring bind lithium, 5-member sodium, and 6-member 6 oxygen atom bind potassium selectively. Cryptant, it is a molecule, one of type of molecule, it can bind potassium ion, ammonium ion. So what you can see the applications is that this supramolecule can detect and bind at molecular level, which is not possible for. So next, I told that how to synthesize these molecules. So one of the most common process is called self-assembly. Self-assembly means where the molecular units, they automatically reorganize to give a symmetric structure. For example, you see my cell. My cell, it is forming from a single unit where it has hydrophobic and hydrophilic unit. So it organizes so that hydrophilic head outside and hydrophilic inside, so it give a spherical structure. DNA, it a double strand structure. By hydrogen bonding, it can form. So similarly, if we give small molecules and a driving force so that it will reorganize to give a definite shape, so that is called the self-assembly process. So there are so many design principles. I will talk just 2-3 examples. So one is hydrogen bond, that DNA, it is like we have seen. So hydrogen bond, using hydrogen bond also, several macro cycle, like 2-dimensional macro cycle. It is not an extended framework, it is discrete molecules. You see, this kind of a hexagonal molecule can be prepared by hydrogen bonding interaction. Next, another important is coordination
architecture. So where you see there is two unit people are using, acceptor and donor. Donor containing organic molecule which have donating site, chelating site, and acceptor has a metal counter and a metal part, and also there we are giving the direction. That means if you take this metal as platinum or palladium, so it has a square planar structure. So if we block one or two positions and open other two positions, then it will directionally bind with the ligand. So this is the strategy. So you see how we can make the 2D and 3D ensembles. So for example, if we take this molecule, this is a palladium or platinum if you think, this is called 0 degree acceptor, like this molecule. Here it is P83, and if you take a nitrate, so nitrate easily can remove. So it will act as a 0 degree linker. So with this, and this is the, if a linear ligand like this, it will give a square like this. So like this way, it can give a several two-dimensional and three-dimensional architectures. Some of examples if you see, people have done this kind of ethane diamine nitrate acceptor, and some this kind of tetrapyridyl ligand. So this molecule, when treated with palladium ethylene diamine palladium nitrate, it is giving a barrel-like of structure. Barrel means all four faces are composed by this ligand molecule, and vertices contains the metal atoms. And it forms in 100% yield sometimes. So we'll go the example, for this example. You see, this is a porphyrin molecule, and 4 pyridine unit is there. When it is bind with ferrocene-based platinum acceptor, it is 90 degree acceptor. See, angle between this is 90 degree. This is 2 leaving group, counter anion. So when it is binding, you see in vertex it can sit, and it can give, and because it is ferrocene, it can expand its bond angle, and it is giving a hexagonal structure. That means a hexagonal barrel. All the 6 phases are composed by this ligand and vertices by the metal. So what is the utility? Why you are doing that? Utility of the means metal coordinated architectures. So because of this, if you see, this molecule contains hydrophobic unit, organic molecule, as well as metal counterparts. So metal counterparts also have high charge. If you see, this platinum is +2 oxidation state. So when this structure is forming, it has, so 12 into +2 means +24 charges. So this make it is water soluble. Instead, it becomes water insoluble, because you know organic molecules are water insoluble. So after forming the cage, this molecule becomes soluble. So I'll show some examples. Let's see this molecule. This is TPE, tetraphenyl ethylene, 4 phenyl group. Tetraphenyl ethylene with 4 imidazole, which can bind by this nitrogen atom. Now this molecule, if you react with tetramethyl ethylene based palladium acceptor, it is an anti acceptor, so it can give a trifacial barrel in 100% yield. So you have to just mix the two counterpart in 50 degrees centigrade in water, just stir in 50 degrees centigrade, keep it for 12 hours or 8 hours. You will get a water soluble compound which is 100% this barrel compound. I will show some characterization technique, so you can check that this is actually forming. And because of forming this structure, you see in water it is soluble, and it has hydrophobic unit, so it can provide a hydrophobic pocket. So you can see a space, no? Inside this, there is a 2 window above and below. So in this, in water, you know, if you now give some guest molecule like this catalysis has done. This is naphthaldehyde with this dimethyl molecule. So now see, these two molecules in water will not react, because in water it is insoluble. But in presence of this architecture, this two is going inside to the barrel. So it is like container, vessel, molecular vessel. And inside this, when it is going, there is proximity. So very quickly, very fast the reaction is going. And once the reaction is going, it is going to bigger size, and it is coming out. So this barrel is acting like a catalyst. by simply giving the reaction space where two substrate can go and react between them. So I will, and next, as I told that I will show some organic example also where this expensive metal pickers are not used. So there are some organic molecules people try to synthesize. Physically it is possible, not like cube and dodecahedron. This has been synthesized, but here the difficulty again was this is CC bond, and it is very difficult to synthesize in 100% scale. So this dynamic covalent chemistry, this concept then solve this problem. So this concept is that if you mix two precursor, it will give product to 100% yield. Why? Because if any other product it is forming, it is dynamic bonds. So it will break and go back to the substrate. Then again it will give to the your desired product. So one of the examples is imine condensation reactions. So imine bond are very reversible. So if it gives something else, it can go back and again it can form your desired structure, symmetrical structure. So okay, so this is some examples people have reported. Okay. So this structure, for example, you can see it is a nano ball kind of structure. This is a crystal structure. So, and the size is around 3 to 4 nanometer of this molecular ball, and they have used this as a active surface molecule where here they have done photooxidation catalysis using these molecules. Like if it contains some photoactive group, like here. So by using this functional groups property, they can use in several applications. So next I'll go one of my work which I've done. So based on this, what I've explained, that coordination architecture structure, I have synthesized this barrel. I could able to synthesize this barrel. Barrel means tetrahedral box actually, where two side is open, two end side. So the idea was again same. It should have a open window so that guest can easily go inside, and after reaction it can go outside. So this was some reaction scheme. So this tetrapyridyl ligand was synthesized by this condensation reaction. So basically this is a thiamide core, and it contains 4 tetrapyridyl units, so which can bind with palladium, and upon reacting with both palladium and platinum acceptor, in both case it is giving a barrel, but unfortunately in one case, for palladium case, we get water insoluble barrels, and for platinum, well, it has more high potential charge, so we got water soluble barrel. And with this, because it is water soluble, we have checked some applications, some host guest chemistry, because I have seen that in earlier case we have seen some guest in aqueous medium can go inside to the barrel. So for that, what guest we have choose? A photochromic guest, like DASA. Photochromic materials, you know, it is very useful. Okay, because in presence of light, it can switch the structure, and by using that property, we can do several materials. So this DASA molecule, this is called donor acceptor Stenhouse adduct. It's basically a amine counterpart in and dicarbonyl counterpart. So this molecule, it gives color change and also structural change by just irradiating visible light, even not UV light. So this is DASA molecule, and by changing solvent. So this one type of photochromic molecule which change their structure, okay, in presence of light or solvent. For example, this linear structure, this is stable in organic solvent because it is organic. And when it is going to another structure, converting, it is dipolar structure, plus minus. So it is not stable in organic. So in organic solvent, you will see red color because it is conjugated. In protic solvent, aqua solvent, you will see a yellow color. So by solvent changing, you can see 2 colors. And also, in organic solvent also, this red solution, if you keep under visible light, slowly you will see yellow color is appearing. Because by light irradiation, this form a deuterionic structure, which is not stable, but it forms by presence of visible light. So this is reversible process in organic solvent. So our idea was, in water, this is not reversible. Why? because this is deuterionic, so it will be very much stable in water, and it will not like to go back the neutral form. This is linear form. So in water, this reversible process become irreversible. So our idea was, can we make this irreversible process in water is reversible by using our barrel. So what we have done, so this is characterization technique. I will not go to that because we don't have time. So, okay, better. Going before that, I will show the crystal structure. So first I have characterized by NMR and mass, and not only that, this is single crystal XRD structure of TBO. We practically have seen that this kind of barrel it is forming, and if you see the dimension, it is like 1 point diagonal. The diagonal diameter is 1.9 to 2 nanometer. We say 2 nanometer diameter it has this barrel. So this barrel has enough molecular pocket to host a molecule. So for that, we have utilized this in this kind of isomerism property. So what I have explained that in this guest, what I have shown, that guest in water it is yellow color because of deuterionic form. So now if you keep in dark, or if you irradiate light, anything if you do, it will not, color will not change, because this is stable deuterionic structure. This is deuterionic structure. What I've done, when we are adding our barrel to this water soluble, so just after adding, it is getting soluble, and after getting soluble, it is giving the red color. So that means the deuterionic form slowly converts to the open form, linear form. And reverse also we have done. We have taken solution of barrel in water, to that in solid state is open, red color, then red solid when we have added, it should go in water, it should go to the yellow color, polar form, but it is being stable inside the barrel, and it is staying in the linear form and giving the red color you can see. So this is the applications, and we have characterized the host guest ratio, other things. Okay, we have done 2D NMR. We have optimized their host guest structure also by doing Deptt analysis. So how the guest can align inside the pocket. And this is the conclusion of this work. And here we have seen that metal coordinator architecture can do some host guest chemistry in water. That is very useful. But the problem is that the metal bond, this is not that much stable. It decomposes in presence of acid base. And also it involves some costly platinum palladium, which have square planar architecture, square planar geometry. So those are very expensive. So I also tried to prepare some purely organic structure, which is very not expensive. It's very cheap materials, aldehyde, amines, those kind of molecules, if we can prepare a large molecular architecture. So for that, first I will show this molecule. This is called some hexaldehyde, like this is isophthaldehyde, and 3 units we have merged here. And here I have tried that imine condensation strategy. So on aldehyde I am forming a prepared, it is building unit, and I have mixed this with this diamine. This is called cyclohexane diamine. So, and we expected a symmetrical structure. So we will see what it is forming actually. And we have seen actually this kind of architectures, tetrahedral cage. It's a big nano cage, around 2 nanometer diameter it is having. And you see all the hexaldehyde, it is situating at the face of the tetrahedron. Like 4 face, a tetrahedron has 4 face, so 4 face it is sitting, and in vertices, so 3 diamine unit is sitting, and giving a tetrahedral structure which have a void inside it. So this characterization technique, I'll not go. I'll also show some Deptt analysis. See this, if you imagine a sphere inside the tetrahedral cage, the diameter is getting 1.34 nanometer, which is not very small, like molecular level. It is giving 1.34 nanometer diameter size. So, and okay, next slide it is there. Oh no. Chirality also. So this is something different, is that this hexaldehyde, it was achiral. After forming cage, it is giving chiral cage. So it is chiral induction, and then chiral induction is happening from the cyclohexane diamine unit. So that cyclohexane diamine we have taken the enantiomer pure, and that enantiomer pure cyclohexanediamine, this one, this is a achiral aldehyde. But after forming cage, this chirality, it has transferred from cyclohexanediamine to cage, and that's why we are getting two enantiomer pure cage. Like if you are taking RR cage, we are getting one isomer. If you are taking SS diamine, we are getting another isomer. So in stereochemistry point of view, we can synthesize a enantiopure cage without using a enantiopure substrate, means aldehyde unit. Anyway, so again, I'll go back to the our main topic, nano material. So here, because it has a pocket, and also it has cyclohexanediamine, means all nitrogen atoms which can complex with metal atoms. So we tried whether we can prepare some complex or nanoparticle, whether this cage can interact with some metal precursor. So what we have done, this cage we have taken in chloroform soluble, and we have added palladium acetate. So here oxygen stage +2 palladium acetate salt. What we have seen, it is giving yellow color, so which signals that some complexation it is forming really. So this, because this cyclohexanediamine unit, it can complex with palladium, so we can see some complexation. And when we are next adding sodium borohydride, it is giving black color. So which indicates that this +2 oxidation state is going to 0 oxidation state, and it is giving black color. Now the question was whether it is nanoparticle, nanomaterial or not. So we exclusively characterize these materials whether it is nanomaterial or not. So oxidation state, particle size, morphology, all we have checked by TEM, SEM and EDX spectroscopy. So this is the TEM. You can see it is forming a homogeneous size of nanoparticles, this black spot, which is having this distribution 3.5 plus minus 0.3 nanometer. So we are getting a nanoparticle with controlled size. So this is very tiny size, and which we can control by using a cage structure. Just simply giving the metal salt, and after reduction it is giving your nanoparticle in very smaller size. And oxidation state also we have checked that it is 0 oxidation state from the 3D by 2 and 3D 5 by 2 value. And this is the morphology. You can see that this is a amorphous material. And next, this nano catalyst, this nanoparticle we have used as catalyst. Because nanoparticle has application in catalysis, so we have checked. Because nanoparticle can do catalysis, so we have checked some catalysis, and this catalysis we got around quantitative yield in DMF water medium under 100 degrees centigrade heating conditions. And we got a quantitative yield, and substrate scope, if you see that all cases we are getting more than around 90% yield for all cases. And not only that, this nanoparticle was stable for recycling also. We have checked three recycling. You can check the yield is changing for first cycle, conversion 99, for 98, 96, like that. So conversion was going to quantitative almost after 3 cycle also. You have checked the material after recycling also, the material TEM image, which show that it is having around 3.6 nanometers. So size is not that much changing, leaching is not happening, and the nanoparticle becomes stable in presence of cage template. So in this case, so we have done the synthesis of cage in quantitative yield from very cheap material, and which able to catalyze this homocoupling reaction, and recyclability also shows a good amount of yield. So in acknowledgement section, I will acknowledge my institute where I have done PhD and masters, and my supervisor, PhD supervisor, Professor P.S. Mukherjee. Now he is associate editor of Inorganic Chemistry Journal. Like that, I'll thank the audience. Thank you. Right, sir. Right, sir. Good point. In all cases, we are checking the stability after reactions also, or after catalysis also. We have checked that cage is not breaking and is stable. Unless the, yeah. So that again, it is coming from the designing principle. I will go to quickly to the designing principles, sir. For example, okay, this, okay, okay. For example, this one. So this acceptor is designed in such a way that it can accommodate 90-degree angle. Square planar metal. So one C side is blocked, another C side is open. So 90-degree angle. And this is a stable molecule which is planar. So in plane it can coordinate. Now it if can hold 90-degree angle and these two can bind, then there is no strain. Because it can hold, because it is like this 90-degree angle and the faces like this, it is binding. So that way, the design principle coordinator architectures, it has designed that some, all are not alloyed, all geometry. So it depends on the donor acceptor binding angle. So based on the angle, it will give the structure which is more stable thermodynamically. Because there are several possibilities when these both are mixed. So this is, that's what is called self-assembly. So it is self-assembled to give a unique one structure. We are not controlling the structure. We are giving the geometry, giving the direction. So in that direction it is forming. Right.
So in that case, when this is forming, why can't this, the same molecule can be part of 2 nanoparticles, right?
Right, sir. Actually, what we thought that nanoparticle will form inside the cage pocket. So actually, we did not see that. So that part, it is good like observation point, sir. So nanoparticle size, if you see, it is 3.5 nanometer. 3.5 nanometer. And diameter, what we have calculated by Deptt, it is 1.34, like if you spare, if you consider. So it is actually, it is actually multi-component, multi-cage are supporting the nanoparticles. So it is vertices, because vertices has the complexation unit. Yeah, for this case, there are also some examples, single cage, inside pocket it can accommodate, because size if you can check, it is smaller size, in annual size is smaller than the pocket. In this case, because the vertices, it is containing the complexation unit, binding unit, so that's why at corner it is forming. And when it is pair it is forming, so other cage also can support from outside. Yeah, like some case we check dozy complexation. Like dozy means a two-dimensional NO spectra, so we can check, can differentiate the molecules based on the diffusion. So when we check the palladium acetate this complex, cage complex, it is showing a single line, means single diffusion coefficient. That means entity is 1. If it's different, it will show 2 different coefficients. Like this is the spectra. Like this is called dozy NMR. For cage I have shown here, like all the cage peaks, these all are cage peaks, these are having in same line, and this is solvent peaks, it is staying in another line. So for dozy also can show on, also IR spectra also we have done, and mostly theoretical, like we are getting experimentally 3 nanometer size, and theoretically when checking it is 1 point less than that, and logically it is 36 only, it is counting the complexes unit. So right, sir. In this case, I have tried, because I told that this is reversible bond. So in some many, because this sometimes breaks actually for this case when it is imine bond. So we could not crystallize this system. Yes. Right, sir. Yeah. Sir, your that is question is for the metal architectures that I have shown in water catalysis is going. So in water, sir, organic molecule in water, it is aqueous environment, so hydrophilic environment. So catalysis, organic molecule of catalysis we are doing, then organic molecule, it is preferring the hydrophobic environment. So in aqueous solvent, it don't want to stay, so it is going inside the pocket, in hydrophobic. Now after reactions, that one example I have shown, the when size is getting bigger, it has open window, so it is, if it is coming out, it is forming precipitate. In water, it is forming precipitate. And now small molecule substance, then again they are coming inside. And also separating how? Because if you adding chloroform in the water, it is forming two layer, and chloroform layer, it is extracting the product. Like this way, this process is going. For these examples, sir, for like last example, nanoparticle, this is heterogeneous catalysis. Our material is heterogeneous, not soluble. So we are just filtering the catalyst, and again we are doing the catalysis. Cage. Yes, definitely by changing the ratio, but actually for ratio is fixed actually. If you check the binding and donating side, that ratio will be fixed. If you add excess, then it will form polymer. We are interested in discrete cages, so that's why we are maintaining the ratio just. Now suppose 2 and 3 unit are joining. Now there are 4, 6 also possibly there. Means 4 unit, 4A, 6B, 8A, 10B. Like that ratio is, if 2 is to 3, then multiple times it can happen. Like 2A unit, 3B unit. Now if you multiply by 2, 4A unit, 6B unit. This is possible. Now which structure it will form, it depends again the angle strain, as I mentioned, angle strain, their stability, those things. Not always. When you are getting single, that system you are focusing. Sometimes various possibilities are there. When one structure is most stable thermodynamically, so that case we are getting 100% conversion. We can, because we cannot separate. This is large molecules. So yes, there are many examples when you are mixing, it is not forming single cage. It is forming mixture. Kinetically, in a thermodynamic, we are focusing on thermodynamic parameters. So most stable cage, if it is giving room temperature, sometimes 60 degrees centigrade, not very high, but we are giving time. Not important here. If kinetic important, then it will give mixture of products. So we're trying to get thermodynamic parameter to be work. Then only we'll get a single unit. So that's why, like this imine cage we are keeping for 3 days, 4 days. Just simply we are rotating and see 4 days. Then we are checking by NMR, by this, whether mixture or single product. When single product, that point we are stopping the reaction, we are isolating the compounds. Right, sir. Yes. Right, sir. Here, one of the example is that this problem. So here I've shown this diamine, trans diamine. It is working with hexaldehyde. It is giving a tetrahedral structure because this geometry, if you see, in vertices, to form the tetrahedral, 3 amine has to sit, and 3 amine, if it sit, it has to be trans, and then it will give tetrahedral. Now, when we have used cis diamine, it does not give a cage. It gave a mixture of products. Suppose 3 units have been stitched, 3 units only reacted. So we did not get, in that case, a single product, mixture of products we got. So in this case, for example, trans only giving the single product. But in enantiomer pure form, trans diamine, RR giving one isomer, SS giving another isomer. Why? Because this orientation, it is directing this orientation. Commercially available. We can also isolate. It is commercially available, not that much, like 5,000 for 25 mg gram. Cis1 we have tried. Cis1 giving mixture. Very broad NMR mixture, many peaks. Right. They're like that one nanoparticle template. As a nanoparticle template, I have used some gas storage, selective gas binding. Like it has a selective pocket. If you change the functions, now we can do several applications. Right, right, sir. Thank you.